Right now, somewhere in the cold dark between galaxies, a star 100 times more massive than our Sun is dying. And when it goes, it will release more energy in a single instant than 1,000,000,000,000 suns will produce in their entire lifetimes. The shockwave will tear through the fabric of space-time itself. Entire solar systems will be sterilized in seconds. And from Earth, if we catch it, if our instruments are pointed in the right direction at the right microsecond, it will look like a brief flash of light, no brighter than a distant street lamp. That explosion, a hypernova, is the most violent stellar death we know of. For decades, we have measured these events and called them the most powerful things in existence. We have built careers cataloging their energy output, modeling their mechanics, watching entire galaxies light up as they fire gamma-ray bursts across billions of light-years. And yet, they are not even close to the most powerful forces in the universe. This video is about what actually rules the cosmos. Not the loudest events or the brightest flares, but the deeper architecture, the silent dominators that shape reality itself. We are going to start with those explosions, with dying stars and colliding black holes, and the kinds of cosmic violence that make hypernovae look tame. But then we are going to pull back, further, deeper, past the explosions, past gravity, past the forces you learnt about in school, all the way down to the scaffold that holds existence together, the invisible power that allows anything, stars, planets, your heartbeat, to happen at all. Because the most powerful thing in the universe is not what you think it is. And by the end of this, you will see why every explosion, every black hole, every atom in your body is just an echo of something far stranger. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Somewhere in the depths of the observable universe, roughly 7 billion light-years from the chair you are sitting in right now, there is a star that is about to die. Not quietly, not slowly, not in the gentle fade that astronomers once imagined all stars undergo when their fuel runs out. This star is going to detonate with such unimaginable force that for a brief, brilliant instant, it will outshine every other star in its galaxy combined, and then it will outshine the galaxy itself. And then, for reasons that still make astrophysicists pause when they talk about it will briefly become one of the brightest objects in the entire observable universe, brighter than 1,000,000,000,000 suns burning at once. We are talking about a hypernova, the most violent stellar explosion physics allows. And to understand what that means, to really grasp the scale of what happens when a star this massive reaches the end of its life, you first need to understand what kind of star we are dealing with. Because this is not our Sun. Our Sun is a middle-aged, middleweight, utterly unremarkable ball of fusing hydrogen, sitting quietly in the suburbs of the Milky Way. It has been doing the same job for about 4.5 billion years, converting 600 billion kilograms of hydrogen into helium every single second, losing about 4 billion kilograms of its own mass to energy in the process. That energy is what lights your day, warms your skin, powers the weather, and makes photosynthesis possible. The Sun is stable. It is predictable. It will keep doing this for another 5 or 6 billion years before it gently swells into a red giant, sheds its outer layers, and fades into a white dwarf. No drama, no explosions, just a long, slow exhale. The star we are talking about is not like that. This star weighs 100 times what our Sun weighs, 100 solar masses. That is not a small difference. That is not like comparing a sedan to a truck. This is like comparing a candle to a blast furnace. Mass changes everything in stellar physics. The more massive a star is, the hotter its core burns, the faster it consumes its fuel, and the shorter its life becomes. Our Sun will live for about 10 billion years. A star with 100 solar masses will live for roughly 3 million years. That is less time than modern humans have existed on Earth. In cosmic terms, stars like this are mayflies. They ignite, they blaze, and they vanish almost immediately. And the reason they die so young is the same reason they die so violently: gravity. When you have that much mass packed into one object, gravity does not politely hold things together. It crushes. The core of a massive star is not a place. It is a pressure cooker running at temperatures and densities that would make the center of our Sun look mild. At those extremes, hydrogen does not just fuse into helium. Helium fuses into carbon. Carbon fuses into neon. Neon into oxygen. Oxygen into silicon. Silicon into iron. Each stage burns hotter and faster than the one before it. Hydrogen fusion in a star like this might last a few million years. Helium fusion, a few 100,000. Carbon, a few hundred. Oxygen, less than a year. Silicon fusion, the final step before iron, lasts about 1 day. 1 day, and then the star runs out of moves. Iron is the end of the line. Fusing iron does not release energy. It costs energy. Once the core fills up with iron, fusion stops. The furnace goes out. And when the furnace goes out, there is nothing left to hold the star up against its own weight. What happens next happens fast. The core, no longer supported by the outward pressure of fusion, collapses. Not over millions of years, not over hours. In less than a second, a core the size of Earth, weighing more than our entire Sun, implodes to a ball roughly 20 kilometers across. 20 kilometers. You could drive across it in 15 minutes if there were roads. The density becomes so extreme that protons and electrons are crushed together into neutrons. The core becomes a neutron star. Or if the star is massive enough, it keeps collapsing past that and becomes a black hole. Either way, the collapse releases a staggering amount of gravitational energy. The infalling outer layers of the star, still racing inward at a significant fraction of the speed of light, slam into the newly formed core and bounce. That rebound drives a shockwave outward through the star's envelope, ripping through thousands upon thousands of kilometers of stellar material in seconds. And as that shockwave moves, it heats everything in its path to temperatures exceeding 1 billion degrees. At those temperatures, the star does not just explode, it disintegrates. The outer layers are not gently pushed away. They are launched into space at velocities approaching 30,000 kilometers per second, 10% the speed of light. The explosion does not just destroy the star, it obliterates it. What was once a coherent object, a star with structure and layers and a core, becomes a rapidly expanding cloud of superheated gas, carrying with it every element the star ever made. Carbon, oxygen, silicon, iron, nickel, all the way up the periodic table. Every atom heavier than helium in your body right now was forged inside a star. Most of those atoms were scattered into space by explosions exactly like this one. You are, quite literally, made of dead stars. The energy release is difficult to describe in terms that make intuitive sense. We do not have everyday experiences that compare. The total energy output of a hypernova in the first few seconds is roughly equivalent to the amount of energy our Sun will produce over its entire 10 billion year lifetime. Except the hypernova releases it all at once. In some cases, for a brief window of time, the explosion can shine with the light of 1 trillion suns. 1 trillion, not a million, not a billion, 1 trillion. If you took every star in 1,000 galaxies like the Milky Way and turned them all on at the same time, you would start to approach the brightness of a single hypernova at its peak. And this is not theoretical. We have seen these events. We have measured them. Astronomers detect supernovae every night. Most of them are ordinary as far as stellar explosions go. A star goes supernova. It brightens for a few weeks, then it fades. We catalogue it, analyze the spectrum, move on. But every so often, we catch one that does not fade the way it should. It stays bright longer. It releases more energy. The explosion is hotter, faster, more luminous than the models predict. Those are the hypernova. The first one we clearly identified was SN 1998 BW, detected in April of that year, in a galaxy about 140 million light-years away. It was associated with a gamma-ray burst, which we will get to, but what stood out immediately was the sheer energy. The explosion was at least twice as powerful as a normal core collapse supernova, possibly more. The star that died was estimated to have been at least 40 solar masses, possibly more than 100. It had rotated rapidly, which funneled some of the explosion's energy into jets that punched through the star's poles at relativistic speeds. The result was an explosion so energetic that it became the template for what astronomers now call a hypernova. We have found others since. SN 2006 GY, which for a time held the record as the brightest supernova ever observed. SN 2016 APES, which released so much energy that some scientists argued it might have been two massive stars colliding and exploding together. As SN 5 LH, detected in 2015, which was so luminous that it defied classification for years. Each one of these events rewrites a small piece of what we thought we understood about how stars die, and each one reminds us that the universe is capable of violence on a scale we can measure but not truly imagine. So what does a hypernova actually do to the space around it? What happens to the neighborhood when a star goes off like a bomb? The first thing to understand is that space is not empty. Even in the voids between stars, there is gas. Thin, cold, mostly hydrogen, but it is there. Around massive stars, especially young ones that have not yet drifted far from the molecular clouds where they formed, that gas can be relatively dense. When the shockwave from a hypernova hits that gas, it does not nudge it, it accelerates it. The shockwave is a wall of energy moving outward at thousands of kilometers per second, and everything in its path gets swept up, compressed, and heated. The gas goes from a few degrees above absolute zero to millions of degrees in an instant. It glows, bright enough to be visible across intergalactic distances. That glowing shell is what astronomers call a supernova remnant, and it can remain visible for thousands of years. The Crab Nebula, one of the most famous objects in the night sky, is the remnant of a supernova that exploded in the year 1054. Chinese and Arab astronomers recorded it. It was visible during the day for weeks. The remnant is still there, still expanding, still glowing. That was a normal supernova. A hypernova leaves behind something even more spectacular. The shockwave does more than heat gas. It compresses it. And when you compress a cloud of gas hard enough, it can collapse under its own gravity and start forming new stars. This is one of the ways star formation propagates through a galaxy. A massive star dies. The explosion triggers the collapse of nearby clouds, and a new generation of stars is born from the ashes of the old one. The cycle repeats. It has been repeating for more than 13 billion years. Without supernovae, galaxies would not look the way they do. Without the heavy elements scattered by these explosions, rocky planets would not exist. Without rocky planets, there would be no place for chemistry to build complexity, no oceans, no continents, no life. The violence is not incidental, it is essential, but the shockwave is only part of the story. The explosion also affects spacetime itself. Mass and energy warp the fabric of space. That is what gravity is. A star sitting quietly in space creates a small dip in spacetime, and that dip is what we experience as its gravitational pull. When a star collapses into a neutron star or a black hole, that dip becomes a well. A steep, deep distortion that does not just pull on nearby objects, but bends the paths of light itself. If the core collapses into a black hole, the distortion becomes so extreme that nothing, not even light, can climb back out. And when the core collapses that violently, that quickly, it does not just create a static distortion, it shakes spacetime. Ripples spread outward from the collapse at the speed of light, stretching and compressing space itself as they pass. These are gravitational waves, and we have only been able to detect them for a few years. The first confirmed detection came in 2015 from the collision of two black holes more than 1 billion light-years away. The signal was tiny. It stretched and compressed the detectors on Earth by less than the width of a proton. But it was there. Since then, we have detected dozens of events. Most of them are black hole mergers. A few are neutron star collisions. We have not yet definitively detected the gravitational wave signal from a supernova or hypernova, but we know it is there. The collapse happens too fast and too violently not to produce one. The problem is distance. Gravitational waves weaken as they spread, and even a hypernova is not quite loud enough in gravitational terms to be easily detected from across the universe. Not yet. But the next generation of detectors, already being planned, should be sensitive enough to catch them. When that happens, we will be able to listen to the core collapse in real time. Not with light, which takes time to escape from the inner layers of the star, but with gravity, which travels at the speed of light and passes through matter like it is not there. We will hear the star die before we see it explode. So here is the picture. A massive star, 100 times the mass of the Sun, has reached the end of its life. Its core has filled with iron. Fusion has stopped. Gravity takes over. In less than a second, the core collapses to a ball 20 kilometers wide. The implosion releases more energy than the star produced in its entire lifetime. A shockwave races outward, tearing the star apart from the inside. The outer layers are launched into space at 10% the speed of light. The temperature spikes past 1 billion degrees. The explosion becomes, for a few brief moments, one of the brightest objects in the observable universe, brighter than 1 trillion suns. The light crosses space for millions or billions of years until it reaches a telescope on a small rocky planet orbiting an unremarkable yellow star in the outer arm of an ordinary spiral galaxy. And someone on that planet points an instrument at the sky, catches a few photons, and realizes what they are looking at. The death of a star so massive, so far away, that its light has been traveling since before complex life existed on Earth. And the explosion is still going. Right now, in some distant patch of sky, a hypernova is happening. The light has not reached us yet. It might not reach us for another 10,000 years, but it is happening. The star is collapsing. The shockwave is racing outward. The core is compressing into something so dense that a teaspoon of it would weigh as much as a mountain. This is the baseline. This is the unit of measurement we are starting with when we ask what the most powerful force in the universe is: a hypernova. A stellar explosion that can briefly outshine an entire galaxy, that can seed a molecular cloud with the elements needed to build planets, that can shake spacetime itself, That is power on a scale that makes human engineering look like scratches in the dirt. But here is the uncomfortable part. As violent as a hypernova is, as incomprehensibly energetic as the death of a massive star can be, it is not the most powerful thing in the universe. It is not even close, because there are events out there that make a hypernova look like a flashlight. There are events out there that make a hypernova look like a flashlight, and the first time humanity detected one, we had no idea what we were looking at. It was July 2nd, 1967. The Vietnam War was escalating. The Cold War was at full boil, and the United States military had a problem. The Soviets had just signed the Partial Nuclear Test Ban Treaty, which forbade nuclear weapons testing in the atmosphere, in space and underwater. The Americans had signed it too, but nobody trusted anybody, so the US Air Force launched a series of satellites called Vela, designed to orbit Earth and watch for the gamma-ray signature of a nuclear detonation. If the Soviets cheated, the satellites would know. The Vela satellites detected something, but it was not coming from Earth, and it was not coming from the Moon. The gamma rays were coming from deep space. The signal was brief, intense, and completely unlike anything a nuclear weapon would produce. The military did not know what to make of it. So they did what any rational organization would do when faced with inexplicable data during a period of extreme geopolitical tension. They classified it and said nothing. For 6 years, the detections kept coming, bursts of gamma rays from random directions in the sky. No pattern, no warning, no obvious source. Finally, in 1973, the data was declassified and published in the Astrophysical Journal. The paper, authored by Ray Clibicedel and his team at Los Alamos, announced the discovery of gamma-ray bursts, events of unknown origin that released more high-energy radiation in a few seconds than the Sun produces in its entire lifetime. The paper did not explain what they were. It could not. Nobody knew. For the next 3 decades, gamma-ray bursts were one of the great unsolved mysteries of astrophysics. They showed up without warning, peaked within seconds, and then faded. Some lasted less than a second, others went on for minutes. They came from every part of the sky with no preference for the galactic plane, which meant they were not coming from sources inside the Milky Way. They were extragalactic, distant, and phenomenally powerful. The problem was figuring out what kind of object could produce that much energy that quickly. A supernova releases enormous amounts of energy, but that energy comes out over days or weeks, not seconds. A neutron star has the density to produce high-energy radiation, but neutron stars are stable. They do not just explode. Black holes can release energy as matter falls in, but black holes do not typically do anything fast. They are patient eaters. They take their time. Gamma-ray bursts did not take their time. They detonated. And the energy output was so extreme that some early estimates suggested they had to be relatively nearby, maybe within our own galaxy, or they would have to be impossibly luminous. If they were truly cosmological, billions of light years away, the numbers did not make sense. The events would have to be releasing as much energy in 10 seconds as the Sun releases in 10 billion years. That seemed absurd. Then, in 1997, the Italian-Dutch satellite Beppo-Sax detected a gamma-ray burst and immediately slewed its X-ray telescope to the same position. For the first time, astronomers caught the afterglow, the fading X-ray and optical light that lingered after the initial burst. Ground-based telescopes picked it up. They measured the redshift. The burst had come from a galaxy more than 6 billion light-years away. The distance was confirmed. The energy output was confirmed. And the absurd numbers were real. Gamma-ray bursts were not just powerful, they were the most powerful explosions in the universe. We now know there are two types, and they come from different sources. Short gamma-ray bursts last less than 2 seconds. They are produced when two compact objects, usually neutron stars or a neutron star and a black hole, spiral into each other and merge. The collision is catastrophic. The objects do not gently combine, they rip each other apart, releasing a flood of neutrons and high-energy radiation. Some of the heaviest elements in the universe, gold, platinum, uranium, are forged in those mergers. The gamma-ray burst is the birth announcement. Long gamma-ray bursts last anywhere from 2 seconds to several minutes. These are tied to the deaths of massive stars, not just any massive star, the very largest ones. Stars with more than 30 or 40 times the mass of the Sun that collapse into black holes and, in the process, launch jets of matter and radiation outward at nearly the speed of light. The jets punch through the star's outer layers and blast into space, carrying with them a beam of gamma rays so concentrated that if you happen to be looking down the barrel of one from across the universe, you will see it clearly. That phrase, looking down the barrel, is not metaphorical. Gamma-ray bursts are not spherical explosions. The energy is not radiated equally in all directions the way a supernova is. It is focused, beamed. The jets are narrow, usually only a few degrees wide. If the jet is not pointed at Earth, we do not see the gamma-ray burst at all. We might see the supernova. We might detect the afterglow in other wavelengths. But the gamma rays themselves, the signature burst, will pass us by entirely. This focusing is why gamma-ray bursts look so powerful. If you took the total energy output of a gamma-ray burst and spread it evenly across the sky, it would still be an extraordinary energetic event. But because the energy is concentrated into a narrow cone, the intensity along that cone is amplified by orders of magnitude. It is the difference between holding a flashlight and holding a laser pointer. Same battery, very different effect. The jets themselves are moving at what physicists call relativistic speeds, not just fast, relativistically fast. Close enough to the speed of light that time dilation and length contraction start to matter. Matter moving at those speeds does not behave the way matter does in everyday life. It carries enormous kinetic energy. When it slams into the gas and dust surrounding the dying star, it heats that material to billions of degrees. The collision produces a shockwave that glows in X-rays and visible light. That is the afterglow. And that afterglow can last for days or weeks, slowly fading as the jet loses energy and the shockwave cools. The longest-lasting gamma-ray burst afterglow ever observed came from an event detected in March 2003. The burst itself lasted about 2 minutes, which made it a long-duration event, but the afterglow did not fade the way most do. It kept glowing. 2 days later, it was still visible. A week later, still there. 2 weeks later, astronomers were still tracking it. That extended visibility gave researchers time to study the event in extraordinary detail. They measured the spectrum. They identified emission lines from heavy elements. They confirmed that the burst was associated with a supernova. The connection between long gamma-ray bursts and the deaths of massive stars was no longer a hypothesis. It was observed fact. One of the most famous gamma-ray bursts ever recorded went off on March 19, 2008. The designation was GRB 080319b. It originated from a galaxy 7.5 billion light-years away. 7.5 billion. The light had been traveling for more than half the age of the universe, and when it arrived, the burst was briefly visible to the naked eye. Not through a telescope, not with a camera. If you had been standing in the right place on Earth, in the dark, Looking in the right direction, you could have seen it. A flicker of light from an explosion so far away that the photons reaching your eye had left their source before the Earth existed. The peak brightness of GRB 080319b was magnitude 5.8. That is dimmer than the faintest stars most people can see from a city, but under a dark sky, away from light pollution, it would have been visible. You would have had to know exactly where to look and exactly when, but it could have been done. A gamma-ray burst, 7.5 billion light-years away, visible without instruments. That is how powerful these events are. And yet, as extreme as gamma-ray bursts are, they are episodic. They happen, they fade, they are over. The jets dissipate, the afterglow dims, the surrounding gas cools and drifts. The burst leaves a mark on the interstellar medium, sure, but the event itself is temporary. There are other objects in the universe that do not turn off. Objects that stay on, burning at luminosities that rival or exceed gamma-ray bursts, not for seconds or minutes, but for millions of years. We call them quasars. The name is short for quasi-stellar object, because when they were first discovered in the 1960s, they looked like stars. Faint blue points of light scattered across the sky, indistinguishable from ordinary stars in photographs, but their spectra were wrong. The emission lines were shifted so far toward the red end of the spectrum that it took years for astronomers to figure out what they were looking at. When they finally did, the implications were staggering. Quasars are not stars, they are galaxies. Or more precisely, they are the cores of galaxies where supermassive black holes are actively feeding. The black holes themselves are invisible, but the material spiraling into them is not. Gas, dust, and entire stars are pulled inward by gravity, compressed into a disk around the black hole. That disk, called an accretion disk, heats up as particles collide, and friction converts kinetic energy into thermal energy. The inner regions of the disk, the parts closest to the event horizon, reach temperatures of millions of degrees. At those temperatures, the disk glows brightly, bright enough to outshine every star in the galaxy around it, bright enough to be visible across billions of light-years of space, bright enough that for decades astronomers did not realize they were looking at galaxies at all. They thought quasars were a new kind of star. It was not until the 1980s, when improved imaging techniques allowed astronomers to see the faint glow of the host galaxy surrounding the bright central point, that the picture became clear. Quasars were not strange stars. They were ordinary galaxies with extraordinarily active cores. The supermassive black holes powering quasars are not small. They weigh millions or billions of times the mass of the Sun. Our own Milky Way has one. It sits at the galactic center, a black hole called Sagittarius A star, weighing about 4 million solar masses. Right now, it is quiet. It is not feeding on much. A small trickle of gas drifts inward, glows faintly in X-rays, and that is it. The Milky Way is not a quasar. It is not an active galaxy. It is dormant. But it was not always dormant. Billions of years ago, when the Milky Way was younger and gas was more abundant, Sagittarius A star was likely much more active. It would have been feeding heavily, glowing brightly, possibly qualifying as a low-luminosity quasar or active galactic nucleus. The energy output from the core would have been vastly greater than it is today, and that energy would have had consequences for the galaxy around it. This is where quasars stop being just interesting objects and start being forces that shape galaxies. The radiation pouring out of an active galactic nucleus does not just light up the surrounding gas, it heats it, it ionizes it, it pushes on it. In the most extreme cases, the radiation pressure is strong enough to drive gas out of the galaxy entirely, launching it into intergalactic space at hundreds or thousands of kilometers per second. This process is called feedback, and it is one of the most important mechanisms regulating how galaxies grow. Without feedback, galaxies would form stars too quickly. Gas would collapse, stars would ignite, and within a few 100 million years, a galaxy would exhaust its entire supply of raw material. Star formation would halt, the galaxy would go dark. That does not happen. Galaxies like the Milky Way have been forming stars steadily for more than 10 billion years. Something is regulating the process, slowing it down, preventing runaway star formation. Active galactic nuclei are part of that something. When a supermassive black hole feeds, the energy it releases heats the gas in the galaxy's core to temperatures too high for star formation. The gas becomes too energetic to collapse. It expands instead. Some of it is driven out in winds. Some of it is held in a hot halo around the galaxy, unable to cool and fall back in. The result is that star formation slows or stops entirely in the core. The galaxy does not run out of gas, it just cannot use it. This sounds like a problem, but it is actually a solution. Feedback prevents galaxies from burning through their fuel too fast. It spreads star formation out over billions of years, allowing galaxies to grow slowly, steadily, and in a way that produces the kinds of structures we see in the universe today. Without feedback, galaxies would look very different. They would be smaller, dimmer, and filled with old red stars instead of young blue ones. The universe itself would look different. Quasars are the extreme end of this process. They are galaxies where the central black hole is feeding so aggressively and releasing so much energy that the feedback effects dominate everything else happening in the galaxy. Star formation is not just slowed, it is shut down. Gas is not just heated, it is expelled. The quasar phase is, in a sense, a galaxy committing self-sabotage. The black hole is eating so much that it chokes off its own food supply. And that is why quasars do not last. They are a phase, not a permanent state. A galaxy can only sustain that level of activity for a few tens or hundreds of millions of years before it runs out of gas to feed the black hole. Once the fuel is gone, the accretion disk fades, the radiation drops. The feedback weakens, the galaxy goes quiet. The black hole is still there, heavier than it was before, but no longer glowing. It waits, dormant, until the next merger, the next infall of gas, the next event that delivers fresh material to the core. Then it lights up again. We know this cycle happens because we see galaxies at every stage. We see quasars in the distant universe, billions of light years away, shining at full power. We see galaxies in the nearby universe with faint active nuclei, black holes that are feeding but not gorging. And we see galaxies like the Milky Way, where the black hole is barely eating at all. The transition from one state to another is driven by the availability of gas. Mergers help. When two galaxies collide, their gas clouds smash together, lose angular momentum, and fall toward the center. That feeds the black hole, that ignites the quasar. The early universe was full of mergers. Galaxies were closer together. They collided more often. Gas was more abundant. Supermassive black holes grew faster. Quasars were everywhere. If you could rewind the universe to a time about 10 or 11 billion years ago, you would see quasars scattered across the sky like streetlights. Not just a few, thousands. The sky would be filled with them. Bright blue, violent cores glowing at the hearts of young galaxies. And those quasars were not just lighting up their own galaxies, they were heating the gas between galaxies. The radiation from quasars does not stop at the edge of the galaxy. It keeps going, ionizing the intergalactic medium, the thin web of gas that fills the space between galaxies. That ionized gas cannot collapse to form new galaxies as easily. It is too hot, too energetic. The quasars, in effect, were sterilizing large regions of space, preventing new galaxies from forming nearby. This is what the chapter title means when it says cosmic firestorms. Not fires in the literal sense. There is no combustion in space. But firestorms in the sense of large-scale energetic events that reshape the environment over vast distances. Quasars were not just bright objects, they were forces. They changed the structure of the early universe. They regulated where galaxies could form, how fast they could grow, and how much gas they could hold on to. Without quasars, the universe would have evolved differently. The galaxies we see today, including our own, would not look the way they do. And here is the part that ties this back to gamma-ray bursts. Both of these phenomena, gamma-ray bursts and quasars, are powered by the same underlying process: gravity, matter falling inward. Whether it is gas spiraling into a supermassive black hole, or the core of a massive star collapsing into a newborn black hole, the energy source is gravitational. Mass being compressed, potential energy being converted into kinetic energy, thermal energy, radiation. Gravity is not just pulling things together, it is powering the brightest, most violent events in the cosmos. A gamma-ray burst releases as much energy in 10 seconds as the sun will release in 10 billion years. A quasar can sustain a luminosity of trillions of suns for millions of years. Both of them are gravity at work, not the gentle gravity that holds you to the ground or keeps the moon in orbit. The extreme gravity that exists near black holes, where space-time is bent so severely that the rules start to break. And if you want to understand what rules the universe, you cannot stop at explosions, you cannot stop at radiation, you have to follow the trail back to the source. You have to ask what is powerful enough to take a star 100 times the mass of the sun and compress its core into a ball 20 kilometers wide in less than a second. You have to ask what is strong enough to hold a disk of gas together around a black hole while that gas is being heated to millions of degrees. You have to ask what force can bend light, slow time, and create regions of space where the concept of escape stops meaning anything at all. The answer is gravity, and the most extreme expression of gravity in the universe is not an explosion. It is not a burst of radiation. It is the object left behind when the explosion is over, the remnant, the devourer, the place where matter goes in and never comes back. A black hole is not a thing in the way most objects are things. It is not made of matter. It does not have a surface you could touch, even hypothetically. It is not a sphere of compressed material sitting in space like a dark star. A black hole is a region, a boundary, a place where the rules governing cause and effect, time and space, break down so completely that the universe itself gives up trying to describe what happens inside. The boundary is called the event horizon, and it is the most important feature of a black hole. Not because anything dramatic happens there. Nothing does. If you were falling toward a black hole and you crossed the event horizon, you would not feel a thing, no wall, no barrier, no sudden jolt. You would not even know you had crossed it, but everyone watching you from a safe distance would see something very different. They would see you slow down as you approached the horizon, your clock ticking slower and slower relative to theirs, until you appeared to freeze in place just above the surface, your image redshifting into darkness. From your perspective, you fell through. From theirs, you never quite made it. Both perspectives are correct. That is what makes black holes so deeply strange. They do not just warp space. They warp the relationship between observers. Inside the event horizon, all paths lead inward. Not most paths, all of them. It does not matter which direction you point your rocket. It does not matter how much fuel you burn. Once you are inside, the center of the black hole is not a place you are moving toward. It is a moment in your future, as inevitable as next Tuesday. You will reach the singularity, the point where all the mass is concentrated and space-time curvature becomes infinite, not because you failed to escape, but because escaping would require moving backward in time, and the universe does not allow that. Black holes come in different sizes, and the size matters more than you might think. At the smaller end, you have stellar mass black holes, the kind that form when a massive star collapses at the end of its life. These typically weigh between a few and a few dozen times the mass of the Sun. Their event horizons are small, a few kilometers to maybe 100 kilometers across. If you fell toward one of these, the tidal forces would kill you long before you reached the horizon. Your feet, being closer to the center of the black hole than your head, would experience stronger gravity. The difference in pull between your feet and your head would stretch you violently. Astronomers call this spaghettification, which is a whimsical name for an extraordinarily unpleasant death. Your body would be pulled into a thin stream of atoms, then molecules, then subatomic particles, all spiraling inward toward the singularity. At the larger end, you have supermassive black holes, the kind that sit at the centers of galaxies. These weigh millions or billions of times the mass of the Sun. Our own Milky Way has one, Sagittarius A star, weighing about 4 million solar masses. The event horizon of a black hole that large is roughly 17 times the diameter of the Sun. You could fit the entire inner solar system inside it. And here is the strange part. If you fell toward a supermassive black hole, you might cross the event horizon without being torn apart. The tidal forces near the horizon of a very large black hole are much weaker than near a small one. You would not feel the stretching until you were well inside, falling deeper toward the singularity. You would have time, not much, but some. Time to look around, to see the distorted light from the universe outside bending into strange patterns around you, before the forces finally became strong enough to rip you apart. There is a third category that sits in between, intermediate mass black holes, weighing hundreds or thousands of solar masses. These are harder to find and harder to explain. We do not have a clear formation mechanism for them. Stellar mass black holes form from collapsing stars. Supermassive black holes grow from smaller seeds, likely over billions of years, fed by mergers and accretion. Intermediate mass black holes do not fit neatly into either story. They are too heavy to come from a single star, and too light to have grown the way supermassive black holes grow. Some might form in dense star clusters where multiple stars collide and merge. Others might be the remnants of black holes from the very early universe, seeds left over from a time when conditions were different. We have Ho candidates, objects that seem to fall into this mass range, but the population is not well understood. They exist in a kind of observational gap, heavy enough to be interesting, light enough to be elusive. What all black holes have in common, regardless of size, is that they are defined entirely by a few external properties: mass, spin, and electric charge. That is it. No other details survive the collapse. It does not matter what kind of star collapsed to form the black hole. It does not matter what elements it was made of, whether it was rotating or stationary, whether it had planets or not. All of that information is erased. Once the event horizon forms, the black hole looks the same as any other black hole, with the same mass, spin, and charge. Physicists call this the no-hair theorem, which is a terrible name for a profound idea. Black holes have no hair, No distinguishing features, no complexity. They are the simplest macroscopic objects in the universe, at least from the outside. That simplicity is deceptive. The physics near and inside a black hole is anything but simple. Time dilation becomes extreme, space stretches, light bends into spirals. And the singularity at the center, where all the mass is concentrated, is a place where general relativity, our best theory of gravity, stops working. The equations break down. They produce infinities, which in physics is usually a sign that you are asking a question the theory cannot answer. What happens at the singularity? We do not know. General relativity cannot tell us. Quantum mechanics might, but we do not have a working theory of quantum gravity yet. So the singularity remains a placeholder. A point on the map marked here be dragons. Black holes do not just sit quietly in space, though. They interact with their surroundings, and those interactions are some of the most energetic processes in the universe. When matter falls toward a black hole, it does not fall straight in. It has angular momentum. It is moving sideways as well as inward, so it spirals, forming a flat disk of gas and dust orbiting the black hole. This is an accretion disk, and it is where things get violent. As material in the disk spirals inward, particles collide. Friction heats the gas. The inner regions of the disk, the parts closest to the event horizon, reach temperatures of millions or even billions of degrees. At those temperatures, the gas glows, not in visible light, though some of that is there. Mostly in X-rays and ultraviolet. The disk becomes one of the brightest objects in the local universe, powered not by fusion or combustion, but by gravity, by matter falling. The energy output from an accretion disk can be staggering. A supermassive black hole feeding at the center of an active galaxy can outshine every star in that galaxy combined. It can shine with the light of trillions of suns, sustained for millions of years. The radiation pressure from that glow is strong enough to push gas out of the galaxy entirely, shutting down star formation across huge regions of space. This is the feedback process we talked about in the last chapter. Black holes are not just eating, they are regulating. They are controlling how galaxies grow. And when a black hole feeds on something large, the results can be spectacular. In 2018, astronomers using the Zwicky Transient Facility at Palomar Observatory detected an unusual brightening in a distant galaxy. The object, catalogued as J2245 plus 3743, sits about 10 billion light-years from Earth. That means the light reaching us left the galaxy when the universe was less than 4 billion years old. The brightness peaked at the equivalent of 10 trillion suns. 10 trillion, that is not a typo. For a brief period, this single object was 30 times brighter than any black hole flare ever observed. The leading explanation is a tidal disruption event. A star, possibly around 30 times the mass of the Sun, wandered too close to the supermassive black hole at the galaxy's center. The black hole itself weighs an estimated 500 million solar masses. As the star approached, the tidal forces, the difference in gravitational pull between the near side of the star and the far side, became strong enough to overcome the star's own gravity. The star was stretched. Then it was torn apart, not exploded, shredded. The outer layers were ripped away and flung into space. The core was pulled into a long streamer of gas that wrapped around the black hole and began spiraling inward. That gas, compressed and heated by friction as it fell, glowed, brightly enough to be visible across 10 billion light-years of expanding space. The flare lasted for months, slowly fading as the gas was consumed or expelled. By the time the light reached Earth, the event was long over. The star was gone. The black hole was slightly heavier, and we had a data set that stretched the models of black hole feeding to their limits. Tidal disruption events are not common, but they are not rare either. Astronomers estimate that in a typical galaxy, a star gets close enough to be torn apart by the central black hole roughly once every 10,000 to 100,000 years. In the observable universe, with hundreds of billions of galaxies, that means these events are happening all the time. Somewhere, right now, a star is being ripped apart. The gas is heating, the flare is brightening, and the light from that event is starting a journey across space that might last billions of years. We cannot see most of these events. They are too far away, or pointing in the wrong direction, or obscured by dust. But every so often, one happens close enough and bright enough that we catch it. And every time we do, it tells us something new about how black holes interact with their environments, how they feed, how they grow, how they shape the galaxies around them. Black holes also interact with each other, and those interactions produce something we can detect even when we cannot see the black holes themselves. When two black holes orbit each other, they create ripples in spacetime, gravitational waves. These are not waves in the usual sense. They are not vibrations traveling through a medium. They are distortions in the fabric of space itself, stretching and compressing distances as they pass. The waves travel at the speed of light, and they carry energy away from the orbiting black holes. As energy is lost, the orbit shrinks. The black holes spiral closer together. The orbital period gets shorter. The gravitational waves get stronger. Eventually, the black holes merge. The collision happens fast, over the course of a few fractions of a second. The space-time around the merging black holes is so violently distorted that the waves produced can be detected across the entire observable universe. Not easily. The stretching and compressing caused by a gravitational wave passing through Earth is smaller than the diameter of a proton. But we have built detectors sensitive enough to measure it. LIGO, the Laser Interferometer Gravitational Wave Observatory, came online in 2015. It detected its first black hole merger within months. The signal was clear. Two black holes, one weighing about 36 solar masses and the other about 29, had spiraled together and merged about 1.3 billion years ago. The collision released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. Not over years, not over days, in a fraction of a second. That energy did not come from matter annihilating or from fusion. It came from gravity, from the warping of spacetime itself. 3 solar masses worth of energy, converted directly into gravitational radiation, radiated outward as ripples that eventually crossed the Milky Way and passed through the detectors in Louisiana and Washington. Since that first detection, LIGO and its partner observatories have detected dozens of black hole mergers. Most of them are in the stellar mass range, black holes weighing a few to a few dozen solar masses. A few are heavier. One merger involved a black hole of 85 solar masses colliding with one of 66 solar masses, producing a final black hole weighing 142 solar masses. That final mass puts it firmly in the intermediate mass range, and it was the first clear confirmation that black holes in that mass range exist. Gravitational wave detections are important because they give us a way to study black holes directly. We do not need to see light from an accretion disk. We do not need to watch a star being torn apart. We can detect the merger itself, measure the masses of the black holes involved, measure how fast they were spinning, and calculate how much energy was released. The waves carry information encoded in their frequency and amplitude, and we can decode that information to reconstruct what happened billions of years ago in a galaxy we cannot even see with a telescope. The next generation of gravitational wave detectors will be even more sensitive. LISA, the Laser Interferometer Space Antenna, is planned to launch in the 2030s. It will consist of 3 spacecraft flying in formation, separated by millions of kilometers, using lasers to measure the distances between them with extraordinary precision. LISA will be sensitive to lower frequency gravitational waves, the kind produced by supermassive black hole mergers. When 2 galaxies collide and their central black holes eventually spiral together, the gravitational waves from that merger will be detectable by LISA from across the universe. We will be able to map the merger history of supermassive black holes to see how they grew, how often they collided, and how much energy they released in the process. Black holes are not the most powerful events in the universe. A gamma-ray burst releases more energy in 10 seconds than a black hole merger releases in gravitational waves. A quasar can sustain a higher luminosity for millions of years than a single tidal disruption event. But black holes are the most powerful objects. They are the places where gravity becomes so strong that it overrides everything else, where space-time curves so sharply that the usual rules stop applying, where matter is compressed to densities that make neutron stars look fluffy, and they are everywhere. Every large galaxy has one at its center. Some galaxies have more than one, the result of mergers that have not yet finished. Stellar mass black holes are scattered throughout galaxies, the remnants of massive stars that died millions or billions of years ago. There could be tens of millions of stellar mass black holes in the Milky Way alone. Most of them are invisible. They are not feeding, they are not glowing, they are just sitting in the dark, waiting for something to fall too close. Black holes are patient. They do not need to hunt. They do not need to chase. They just exist, and eventually, over enough time, something will wander near, a star, a gas cloud, another black hole. When it does, gravity takes over. The object is pulled in, torn apart if it is fragile enough, compressed and heated if it survives the approach. Energy is released, light is emitted, gravitational waves ripple outward, and the black hole, now slightly heavier, continues waiting. This is what makes black holes different from every other powerful phenomenon we have talked about. A supernova happens once. A gamma-ray burst lasts seconds. A quasar phase lasts millions of years and then ends. But a black hole, once formed, is effectively permanent. It does not decay. It does not run out of fuel. It does not fade. It just grows, slowly, patiently, inevitably. Every bit of matter that falls in adds to its mass. Every merger with another black hole makes it heavier. Over billions of years, black holes will be the last massive objects left in a cold, dark, expanding universe. Long after the stars have all died and the galaxies have drifted too far apart to see each other, black holes will remain, waiting, accreting the occasional stray particle, radiating faint Hawking radiation over timescales so long that the numbers stop having meaning. But we are not there yet. Right now, the universe is young, active, full of matter and energy and events that reshape the fabric of space on scales we are only beginning to measure. Black holes are part of that activity. They are not separate from the universe. They are woven into it. They regulate how galaxies grow. They produce some of the brightest signals we can detect. They merge and send waves through space-time that we can measure with lasers and mirrors and extraordinarily sensitive instruments. They are, in a very real sense, the universe talking to itself about gravity, about what happens when mass is compressed past every known limit, about what lies at the bottom of the deepest wells in space-time. And those wells are not just steep, they are dynamic, they are moving. They are interacting with the space around them in ways that go far beyond simple attraction. When a massive object moves through space, it drags spacetime along with it. When it spins, it twists spacetime into a spiral. When it merges with another massive object, it shakes spacetime hard enough that the ripples can be felt across the universe. Gravity is not a static force. It is not just pulling things together. It is bending, twisting, stretching, and compressing the very stage on which all other forces play out. And if you want to understand what really rules the universe, you have to understand that stage. You have to look at spacetime itself, at the fabric that connects every point in the cosmos, and ask what is happening to it. Because it turns out the universe is not just expanding, it is accelerating. And the thing driving that acceleration is not gravity, it is something else, something stranger, something that is, right now, pushing the entire universe apart faster than anything we have ever seen. Something that is, right now, pushing the entire universe apart faster than anything we have ever seen. And the thing driving that acceleration is not gravity, at least not gravity in the way we usually think about it. It is something else, something that does not pull, it pushes. And it has been pushing for billions of years, quietly, steadily, accelerating the expansion of space itself. We call it dark energy, and it is the most abundant thing in the universe. It makes up roughly 68% of everything that exists, and we have absolutely no idea what it is. Before we get to what dark energy is doing, we need to rewind and talk about what gravity actually is. Because for most of human history, we got it wrong. Isaac Newton, working in the 1600s, described gravity as a force, an invisible pull between objects with mass. The more massive the objects, the stronger the pull. The farther apart they are, the weaker it gets. His equations worked beautifully. They predicted the orbits of planets, the motion of comets, the tides. For more than 2 centuries, Newtonian gravity was considered complete, a solved problem. Then Albert Einstein came along and said, "No, that is not what gravity is. Gravity is not a force pulling objects toward each other. It is the shape of space itself. Mass does not reach across empty space and tug on other masses. Mass bends the space around it, and objects moving through that bent space follow curved paths. It is the difference between saying a ball rolls toward you because you are pulling on it with an invisible string, and saying the ball rolls toward you because you are standing in a depression in the floor and the ball is just following the slope. Same outcome, completely different mechanism. Einstein published his general theory of relativity in 1915, and it changed everything. Space and time were not separate, fixed backgrounds on which events happened. They were part of the system. A single 4-dimensional fabric called spacetime that could be stretched, compressed, twisted, and warped by the presence of mass and energy. The equations were elegant and deeply strange. They predicted things that seemed impossible, that light would bend around massive objects, that time would run slower in strong gravitational fields, that the universe itself could be expanding or contracting. Nobody believed the expanding universe part at first, not even Einstein. The idea seemed absurd. The universe was supposed to be static, eternal, unchanging. So Einstein added a term to his equations, a cosmological constant, specifically to cancel out the expansion and keep the universe still. He later called it his biggest blunder, because a decade after he published the theory, Edwin Hubble pointed a telescope at distant galaxies and found that they were all moving away from us. The farther away they were, the faster they were receding. The universe was not static, it was expanding. And it had been expanding for billions of years. Einstein's equations, without the cosmological constant, predicted that expansion naturally. The universe started small, dense and hot. It exploded outward in the event we now call the Big Bang, and it has been expanding ever since. For decades, the big question in cosmology was whether that expansion would continue forever or whether gravity would eventually win, slow the expansion down, and pull everything back together into a big crunch. The answer depended on how much matter was in the universe. Enough matter, and gravity would reverse the expansion. Not enough, and the universe would keep expanding forever, gradually cooling and spreading out until it became a cold, dark, lifeless void. Astronomers spent decades trying to measure the total mass of the universe, adding up stars and gas and dust, trying to figure out which fate awaited us. And then in the late 1990s, two independent teams of astronomers made a measurement that should have settled the question. They were studying Type 1a supernovae, a specific kind of stellar explosion that always reaches roughly the same peak brightness. Because these supernovae are so predictable, you can use them as cosmic distance markers. Measure how bright one looks from Earth, compare that to how bright it should be, and you can calculate how far away it is. Combine that with how fast it is moving, determined by the redshift of its light, and you can map the expansion history of the universe. Both teams expected to find that the expansion was slowing down. Gravity, pulling on everything, should have been acting as a brake. The distant supernovae, whose light had been traveling for billions of years, should have been moving slower than the nearer ones. That is not what they found. The distant supernovae were dimmer than expected. Not by a lot, but enough to matter. Dimmer meant farther. Farther meant the universe had expanded more than it should have if gravity were the only thing at work. The expansion was not slowing down. It was speeding up. That result, published in 1998, earned the leaders of those teams the Nobel Prize in Physics. It also created a crisis, because if the expansion is accelerating, something is pushing, and nothing in the standard model of physics pushes on that scale. Gravity pulls. Electromagnetism is too weak and cancels out over large distances. The strong and weak nuclear forces only work at subatomic scales. There is no known force that could be driving galaxies apart faster and faster over billions of years, and yet that is exactly what the data showed. Physicists dusted off Einstein's cosmological constant, the term he had added to keep the universe static and then abandoned. It turned out that term was not wrong, it was just premature. If you put it back into the equations with the right value, it acts as a kind of anti-gravity. Not a force that pulls, but a property of space itself that pushes outward. The more space you have, the stronger the push. As the universe expands, more space is created, which means more dark energy, which means a stronger push, which means faster expansion. It is a runaway process, and it has been running for roughly the last 5 or 6 billion years. Nobody knows what dark energy is. That name is a placeholder. It is not dark in the sense that dark matter is dark, invisible but detectable by its gravitational effects. Dark energy is something else. It does not clump. It does not interact with matter or light. It just exists, uniformly, filling all of space, exerting a constant outward pressure. The leading idea is that it is a property of the vacuum itself, a kind of baseline energy that space has even when it is completely empty. Quantum field theory predicts that the vacuum should have energy, but when physicists calculate how much, the number they get is 10 to the power of 120 times larger than what we actually observe. That is not a small discrepancy. That is the worst prediction in the history of physics. So we know dark energy is there. We can measure its effects. But we have no idea what it is or why it has the value it does. What we do know is that dark energy is winning. Right now, the universe is about 70% dark energy, 25% dark matter, and 5% ordinary matter. Everything you can see, every star, every planet, every galaxy, every atom in your body makes up 5% of the total. The rest is dark matter and dark energy is the dominant component. It is driving the expansion, and that expansion is accelerating. Galaxies that are not gravitationally bound to each other are moving apart faster than the speed of light, not through space. Space itself is expanding, carrying them along. And the farther apart they get, the faster they move. That has consequences. Right now, we can see galaxies out to about 46 billion light-years in every direction. That is the edge of the observable universe. Not because nothing exists beyond that, but because the light from anything farther away has not had time to reach us yet. But because the universe is accelerating, there are galaxies we can see today whose light will never reach observers in the far future. Space is expanding so fast that the light from those galaxies, even though it is traveling toward us at the speed of light, is losing ground. The space between us and them is growing faster than light can cross it. Those galaxies are receding beyond what astronomers call the cosmic event horizon. Once they cross that boundary, they are gone, permanently. No signal from them will ever reach us again. This is already happening. There are galaxies visible in our telescopes today that will fade from view over the next few billion years, not because they are dying, but because space is carrying them away faster than their light can reach us. In a few 100 billion years, an observer in the Milky Way, assuming the Milky Way still exists, will look out into the universe and see almost nothing. A few nearby galaxies, gravitationally bound into a local cluster, and beyond that, darkness. No distant galaxies, no cosmic microwave background, no evidence that the universe is expanding or that it ever had a Big Bang. All the evidence we are using right now to understand cosmology will have disappeared over the horizon. Future civilizations, if they arise, will have no way to know that the universe is larger than what they can see. They will think they live in an island of a few galaxies surrounded by infinite empty space. They will be wrong, but they will have no way to know it. We are living in a brief window of cosmic history where the evidence is still visible. The universe is old enough that galaxies have formed and structure has developed, but young enough that we can still see the distant galaxies and the afterglow of the Big Bang. In another few 100 billion years, that window will close. The universe will still be here. It will still be expanding. But the evidence will be gone, carried away by dark energy's relentless push. The question everyone wants answered is what happens next. If dark energy stays constant, the universe will keep expanding forever, cooling and spreading out until it reaches what physicists call heat death. The stars will burn out, galaxies will drift apart, black holes will evaporate. Eventually, after an incomprehensibly long time, the universe will be cold, dark, and empty. Nothing will happen anymore because there will be no energy left to make anything happen. That is the big freeze. Slow, quiet, inevitable. But there is another possibility, and it is worse. If dark energy is not constant, if it gets stronger over time, the expansion will not just continue. It will accelerate faster. Space will expand so quickly that it will start ripping things apart. First, galaxy clusters will unbind, then galaxies, then solar systems, then planets, then molecules, then atoms. Finally, space-time itself will be torn apart in an event called the Big Rip. One estimate, based on a model where dark energy strengthens over time, puts that end at about 22 billion years from now. We are currently about 13.8 billion years into the universe's life, so that would give us another 8 or so billion years before everything is shredded. That is a long time by human standards. It is not a long time cosmically. We do not know if the Big Rip will happen. Current observations suggest that dark energy is constant, or close to it, which would mean the Big Freeze is more likely. But the measurements are not precise enough to rule out other possibilities. Dark energy could be changing. It could be getting stronger. It could, in theory, even be getting weaker, though there is no evidence for that. We are still trying to figure out what it is, let alone what it is going to do. What makes dark energy especially strange is that it does not do anything on human scales, or planetary scales, or even galactic scales. Gravity is much stronger locally. The Milky Way is not expanding. The solar system is not expanding. You are not expanding. Dark energy is only relevant on the largest scales, where gravity has finished clumping matter into galaxies and clusters, and the space between those structures is mostly empty. In those voids, where there is no mass to generate a gravitational pull, dark energy dominates. It pushes, and the bigger the void, the stronger the push. This is why the universe has structure. After the Big Bang, tiny fluctuations in the density of matter, quantum ripples blown up to cosmic scales by inflation, created regions that were slightly denser and regions that were slightly less dense. The denser regions collapsed under their own gravity, pulling in more matter, forming stars and galaxies and clusters. The less dense regions expanded, pushed apart by dark energy, becoming voids. Over billions of years, this process created what astronomers call the cosmic web, a vast network of filaments and walls of galaxies surrounding enormous empty voids. The filaments are where the matter is. The voids are where dark energy is winning. If you could map the entire universe, not just the part we can see, but all of it, you would see this structure everywhere. Long, thin filaments of galaxies stretching across hundreds of millions of light years, connecting at dense nodes where galaxy clusters form. Between those filaments, voids, huge empty bubbles of space, hundreds of millions of light years across, with almost nothing in them. No galaxies, no stars, just a thin scattering of hydrogen atoms and dark energy pushing outward. The structure looks organic, like a sponge or a neural network. It is the largest pattern in nature, shaped by the interplay of gravity pulling and dark energy pushing. Gravity does not just pull objects together. It bends space, and when space is bent, light traveling through it follows the curve. This is gravitational lensing, and it is one of the most powerful tools astronomers have for studying the universe. When light from a distant galaxy passes near a massive object, a galaxy cluster for example, the cluster's gravity bends the light. From Earth, the distant galaxy appears distorted, stretched into arcs, or even split into multiple images. By studying those distortions, astronomers can map the distribution of mass in the cluster, and when they do, they find that most of the mass is not in the galaxies, it is in dark matter. Invisible, detectable only by how it bends light. Gravitational lensing works because spacetime is not a passive stage, it is part of the system. Mass tells spacetime how to curve. Curved spacetime tells light how to move. The more mass, the more curvature. The galaxy cluster, weighing quadrillions of solar masses, creates a deep well in spacetime. Light passing through that region does not travel in a straight line. It follows the curve. And because we see light as traveling in straight lines, the galaxy behind the cluster appears to be in a different position than it actually is. The image is distorted, magnified, sometimes duplicated. This is not a subtle effect. Some of the most famous images from the Hubble Space Telescope and the James Webb Space Telescope show gravitational lensing in action. Distant galaxies stretched into long, thin arcs, wrapped around the foreground cluster like light bending around a glass lens. Except there is no glass, there is just curved space. And by measuring how much the light is bent, astronomers can calculate how much mass is doing the bending. When they do that calculation, they find that the visible matter in the cluster, the stars and gas, accounts for only about 15% of the total mass. The rest is dark matter, invisible, spread throughout the cluster in a halo that extends far beyond the visible galaxies. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at all, as far as we can tell. The only way we know it is there is through its gravitational effects. It bends light. It holds galaxies together. It shapes the large-scale structure of the universe. And it outweighs ordinary matter by a factor of 5 to 1. If you added up every star, every planet, every atom of gas in every galaxy in the observable universe, and then multiplied that by 5, you would get the total amount of dark matter. It is the scaffolding, the framework, the invisible structure that holds everything else in place. Without dark matter, galaxies would not exist. The visible matter alone does not have enough mass to hold a galaxy together. Stars orbit the galactic center too fast. They should be flung out into space by centrifugal force, but they are not, because there is more mass than we can see. Dark matter provides the extra gravity needed to keep the galaxy intact. It forms a halo around the visible disk, extending far beyond the outermost stars, holding everything together. We do not know what dark matter is made of. The leading candidate is a type of particle that does not interact with light or ordinary matter except through gravity. Physicists call these WIMPs, weakly interacting massive particles. Experiments have been running for decades, trying to detect them directly, looking for the faint signal that would be produced if a dark matter particle collided with an atomic nucleus in a detector. So far, nothing. No confirmed detection. Either the particles are even more elusive than we thought, or dark matter is something else entirely. Modified gravity, primordial black holes, some exotic form of matter we have not imagined yet. The search continues. But whatever dark matter is, it is not doing what dark energy is doing. Dark matter pulls, it clumps, it forms structure. Dark energy pushes, it spreads, it smooths. And on the largest scales, dark energy is stronger. That is why the universe is accelerating. Gravity, even with all the dark matter, is not enough to reverse the expansion. Dark energy is winning. And it will keep winning, pushing the universe apart, faster and faster, until the galaxies disappear over the horizon and the cosmic web unravels into isolated islands of matter drifting through an ever-expanding void. This is the quiet power, not explosions, not radiation, not jets screaming across space at relativistic speeds, just the steady, patient, relentless expansion of space itself, driven by something we cannot see, cannot touch, and do not understand. Dark energy is not dramatic. It does not flare. It does not burst. It does not even change, as far as we can tell. It just is. A constant pressure woven into the fabric of space, pushing everything apart. And because space is everywhere, dark energy is everywhere. It is the majority of the universe, and it is in control. Gravity bends space-time into wells. Dark energy stretches it flat. Gravity builds galaxies. Dark energy pulls them apart. Gravity creates black holes. Dark energy pushes the universe toward a cold, empty future where black holes will be the last remnants of structure. evaporating slowly over timescales so long that the current age of the universe is a rounding error. Both forces are fundamental. Both shape the cosmos. But in the end, on the largest scales, dark energy wins. And yet gravity is not done. It still holds the galaxies together. It still shapes the cosmic web. It still keeps stars in orbit and planets circling suns. And most importantly, it still holds the invisible scaffolding in place, the dark matter halos, the structure that gave galaxies a place to form, the framework that turned tiny fluctuations in the early universe into the stars and planets and life we see today. Without dark matter, none of this would be here. The universe would be smooth, diffuse, empty. Dark energy would have won from the start. But dark matter got there first. It clumped, it collapsed, it built the scaffolding, and everything else grew from that. And everything else grew from that. But here is the thing nobody tells you when you first learn about the universe. When you add up all the stars, all the planets, all the gas clouds, all the dust scattered between the galaxies, all the black holes, all the neutron stars, every single atom of ordinary matter in the observable universe, you only get about 5% of what is actually out there. 5%. The rest is something else, something we cannot see, something that does not glow, does not shine, does not interact with light in any way we can measure directly. And yet it is there. We know it is there because we can see what it does. We can watch it hold galaxies together. We can measure how it bends light. We can map its influence across billions of light years of space. We call it dark matter, and without it, nothing you see in the night sky would exist. The problem showed up in the 1930s, long before anyone was ready to deal with it. A Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a large group of galaxies about 300 million light-years from Earth. He wanted to know how much mass the cluster contained. The straightforward way to do that is to add up the light from all the galaxies, estimate how many stars that represents, and calculate the total mass. Zwicky did that. Then he did something else. He measured how fast the galaxies were moving. Galaxies in a cluster are not stationary. They orbit the center of mass of the cluster, held together by gravity. The faster they move, the more mass is required to keep them from flying apart. It is the same principle that keeps planets in orbit around the Sun. If the Sun suddenly lost half its mass, Earth would drift away. The gravity would not be strong enough to hold it. Zwicky measured the speeds of the galaxies in the Coma cluster and did the math. The galaxies were moving so fast that the cluster should have torn itself apart billions of years ago. The visible mass was nowhere near enough to hold it together. He calculated that the cluster needed about 400 times more mass than he could see. 400 times. He called it dark matter, missing mass, hidden mass. The term did not catch on immediately. Most astronomers assumed Zwicky had made a mistake. Maybe the galaxies were not moving as fast as he thought. Maybe his distance estimates were wrong. Maybe there was a lot of dim matter, faint stars or gas clouds that he had missed. The measurements were difficult. The tools were limited. It was easy to assume the problem would go away with better data. It did not. In the 1970s, an American astronomer named Vera Rubin was studying the rotation curves of spiral galaxies. A rotation curve is a graph that shows how fast stars and gas are orbiting at different distances from the galactic center. In a typical spiral galaxy, most of the visible mass is concentrated in the center. The stars are densest there. The light is brightest there. So you would expect that stars farther out, in the dim outer regions of the galaxy, would orbit more slowly, just like planets in the solar system. Mercury orbits the Sun much faster than Neptune because Mercury is closer to where most of the mass is. The farther out you go, the weaker the gravity, the slower the orbit. That is what Newton's laws predict. That is what every solar system does. Galaxies do not do that. Rubin and her collaborators measured the rotation speeds of stars in dozens of spiral galaxies, all the way out to the edge of the visible disk and beyond. What they found was that the stars were not slowing down. The rotation curve stayed flat. Stars at the outer edge of the galaxy were moving just as fast as stars much closer to the center. In some cases, the speeds were even increasing slightly. That should not be possible unless there is more mass out there, a lot more. Mass that extends far beyond the visible edge of the galaxy, holding those outer stars in their orbits. The only explanation that fit the data was that galaxies are embedded in halos of dark matter. Huge spherical clouds of invisible mass surrounding the visible disk, extending 2 or 3 times farther out than the stars. The dark matter does not glow. It does not form stars. It does not even clump into dense clouds the way gas does. It just sits there, spread out in a smooth halo, providing the gravity needed to keep the galaxy intact. Rubin's work was meticulous. She measured galaxy after galaxy. The pattern held. Flat rotation curves everywhere. Every spiral galaxy she looked at had the same problem. Too much speed, not enough visible mass. This was not a small correction. The dark matter halos were not adding 10 or 20% to the mass budget. They were adding 5 to 10 times as much mass as all the visible stars and gas combined. In a typical spiral galaxy, the stars, the planets, the gas clouds, everything you can see make up about 15 to 20% of the total mass. The rest is dark matter. Invisible, undetectable, except through gravity. And it is not hiding in some distant corner of the galaxy. It is everywhere. The Sun is moving through a dark matter halo right now. So is Earth. So are you. Dark matter particles, whatever they are passing through your body every second. Trillions of them. They do not interact with your atoms, so you do not feel them. They do not bounce off. They do not scatter. They just pass straight through as if you are not there. The most dramatic evidence for dark matter came in 2006 from an object called the Bullet Cluster. This is not a single galaxy. It is 2 galaxy clusters that collided. Clusters are enormous. They contain hundreds or thousands of galaxies, all bound together by gravity. When 2 clusters collide, the galaxies themselves do not hit each other. Space is mostly empty. The galaxies are tiny compared to the distances between them. So during a collision, the galaxies pass through each other mostly unscathed. But the hot gas between the galaxies does not. Galaxy clusters contain vast amounts of gas, far more mass in gas than in stars. When the clusters collide, that gas slams together, heats up, and glows in X-rays. The collision is violent. The gas slows down, piles up, and stays near the collision site. Astronomers observed the Bullet Cluster with X-ray telescopes and saw exactly that, a giant cloud of superheated gas sitting between the 2 clusters, glowing brightly, marking the point of impact. Then they did something else. They used gravitational lensing to map where the mass actually is. Lensing does not care whether mass is visible or invisible. It just measures gravity. Bend light, and you can see where the mass is. When they made that map, they found something extraordinary. Most of the mass was not where the gas was. It was where the galaxies were. The dark matter halos around the galaxies had passed straight through each other, unaffected by the collision, because dark matter does not interact with itself the way gas does. It does not collide. It does not slow down. It is collisionless. The gas stayed behind, glowing in X-rays. The dark matter kept moving, carrying the galaxies with it. This was the smoking gun. You could see the separation, gas in one place, mass in another. If dark matter did not exist, the mass should have been where the gas was. It was not. The mass was elsewhere, invisible, detectable only by how it bent light from galaxies far behind the cluster. The bullet cluster was direct observational evidence that most of the mass in the universe is something other than the ordinary matter we are made of. Dark matter is not just sitting around doing nothing. It is not passive. It is the reason galaxies exist in the first place. In the early universe, just after the Big Bang, matter was spread almost uniformly. Almost. There were tiny fluctuations, quantum ripples blown up to cosmic size during inflation, that created regions slightly denser than average and regions slightly less dense. Those fluctuations were tiny, 1 part in 100,000, but they were enough. Gravity amplified them. Dense regions pulled in more matter. Less dense regions lost matter. Over time, the dense regions collapsed into clumps. Those clumps became the seeds of galaxies. But here is the problem. Ordinary matter, the protons and electrons and neutrons that make up atoms, interacts with light. In the early universe, the radiation was so intense that it kept pushing ordinary matter around, smoothing out the clumps before they could collapse. Ordinary matter could not collapse into galaxies on its own, not fast enough, not in the time available. But dark matter does not interact with light. Radiation does not push on it. So while ordinary matter was being buffeted by photons, dark matter was quietly collapsing under its own gravity, forming the first structures. Dark matter clumped first. It created gravitational wells. And once those wells were deep enough, ordinary matter fell into them. The dark matter halos became the scaffolding, the framework that allowed galaxies to form. Simulations of structure formation bear this out. If you run a computer model of the universe starting from the Big Bang and include only ordinary matter, galaxies do not form the way we observe them. The structures are too small, too late, too diffuse. But if you add dark matter, 5 times as much mass as ordinary matter, the simulation matches reality. Galaxies form at the right times, in the right places, with the right sizes. The cosmic web emerges naturally, with filaments of dark matter connecting clusters and surrounding voids. Dark matter is not just a detail, it is the foundation. Without it, the universe would be a thin soup of hydrogen and helium, with no stars, no planets, no complexity. So what is it? What is dark matter actually made of? That is the question physicists have been trying to answer for decades. The honest answer is, we do not know. We have candidates. We have hypotheses. We have experiments running right now trying to detect it. But we do not have a confirmed detection. Not yet. The leading candidate for a long time has been WIMPs, weakly interacting massive particles. The name describes the properties. Massive, meaning they have significant mass, probably 10 to 100 times the mass of a proton. Weakly interacting, meaning they do not interact through the electromagnetic force or the strong nuclear force. They only interact through gravity and possibly the weak nuclear force, which is why they are so hard to detect. WIMPs fit naturally into extensions of the standard model of particle physics. Theories like supersymmetry predict the existence of particles with exactly these properties. If supersymmetry is real, WIMPs should exist, and if they exist, they should be everywhere. The universe should be full of them, left over from the Big Bang, drifting through space, passing through planets and stars without leaving a trace. Detecting a WIMP requires extraordinary sensitivity. The idea is to set up a detector in a deep underground laboratory, shielded from cosmic rays and other background radiation, and wait for a dark matter particle to collide with an atomic nucleus in the detector. The collision would be rare. A detector the size of a car might see one event per year, but it would produce a tiny flash of light or a faint vibration, something measurable. Experiments like Xenon, Lux, and CDMS have been running for years, using tons of ultra-pure material and waiting for that signal. They have set increasingly stringent limits on what WIMPs could be. If WIMPs exist and interact the way the simplest models predict, they should have been detected by now. They have not been. The experiments keep running, the detectors keep getting more sensitive, and the allowed parameter space keeps shrinking. Either WIMPs are more elusive than expected, or they are not the answer. Other candidates exist. Axions are another hypothetical particle, much lighter than WIMPs, predicted by some theories that try to solve problems in quantum chromodynamics. Axions would interact even more weakly than WIMPs, but there would be vastly more of them. Some estimates suggest the local dark matter density could be dominated by a swarm of ultra-light axions, trillions of them passing through every square centimeter every second. Detecting axions requires different techniques, often involving strong magnetic fields that could convert axions into photons under the right conditions. Experiments like ADMX are searching for this signal. So far, nothing. There is also the possibility that dark matter is not a new particle at all. Maybe it is something we already know about, just in a form we had not considered. MACHOs, massive compact halo objects, were proposed in the 90s as a candidate. These would be things like brown dwarfs, rogue planets, black holes, neutron stars, objects made of ordinary matter but too dim to see. Surveys looked for MACHOs by watching for gravitational microlensing, the brief brightening of a distant star when a massive object passes in front of it. They found some MACHOs, not enough. Nowhere near enough to account for the total dark matter. MACHOs can only explain a small fraction of the missing mass. Most of it has to be something else. Primordial black holes have made a comeback as a candidate. These would be black holes that formed in the first fraction of a second after the Big Bang, not from collapsing stars, but from density fluctuations in the early universe. If they exist, and if they have the right mass range, they could make up some or all of the dark matter. The problem is that constraints from various observations, lensing surveys, cosmic microwave background data make it difficult for primordial black holes to account for all of it. They might contribute, they might not. The jury is still out. Then there are the more exotic ideas, sterile neutrinos, hidden sector particles, mirror matter, self-interacting dark matter that is not cold but warm, affecting structure formation on small scales. Every few years, a new candidate gets proposed, a new experiment gets designed, and the search continues. The frustrating part is that we know dark matter is there. The evidence is overwhelming. Rotation curves, galaxy clusters, the bullet cluster, gravitational lensing, the cosmic microwave background, large-scale structure simulations, all of it points to the same conclusion. There is 5 times as much dark matter as ordinary matter, and it is holding the universe together, but we cannot isolate it, we cannot capture it. We cannot even be completely sure what kind of thing it is. Some researchers have suggested that maybe we are wrong about gravity. Maybe there is no dark matter. Maybe gravity just works differently on large scales than general relativity predicts. Modified Newtonian dynamics, or MOND, was proposed in the 80s as an alternative. The idea is that at very low accelerations, the kind you find in the outer regions of galaxies, gravity is stronger than Newton's law predicts. Stronger gravity means you do not need dark matter to explain the flat rotation curves. MOD works surprisingly well for spiral galaxies. It predicts the rotation curves with impressive accuracy using only the visible matter, but it struggles with galaxy clusters. And it completely fails to explain the bullet cluster, where the mass and the gas are clearly separated. MOD cannot separate mass from matter. Dark matter can. So while MOND is an interesting idea, it does not fit all the data. Dark matter does. The search for dark matter is one of the biggest efforts in modern physics. Detectors deep underground. Particle colliders smashing protons together at near light speed, hoping to create dark matter particles in the collisions. Space telescopes looking for indirect signals, gamma rays or other radiation that might be produced when dark matter particles collide and annihilate. Observations of dwarf galaxies, which are almost entirely dark matter with very few stars, offering a cleaner laboratory to study dark matter's effects. Every avenue is being explored. Billions of dollars, thousands of researchers, decades of effort. And still nothing definitive. But absence of evidence is not evidence of absence. Dark matter is out there. We can see its effects. The fact that we have not detected the particle yet does not mean it does not exist. It means it is even harder to detect than we thought. The universe is under no obligation to make things easy for us. What makes dark matter so powerful in the context of this video is not that it explodes or radiates or does anything violent. It does not. Dark matter is silent, it is invisible. It does nothing except exist and exert gravity, and that is enough. Gravity from dark matter shaped the cosmic web. It seeded the first galaxies. It holds galaxy clusters together. It bends light across billions of light years. Without dark matter, the universe would be a formless void. No structure, no stars, no life. Dark energy might be pushing the universe apart, but dark matter is what built the universe in the first place, and it is still here, right now. Dark matter particles are streaming through the Earth, through the walls of your house, through your body. Trillions of them every second, moving at hundreds of kilometers per second, completely unaware that you exist. You are transparent to them. They pass through the atoms in your body the way light passes through glass, without slowing, without scattering, without leaving any trace. The only interaction they have with ordinary matter is gravity, and on the scale of a human body, that interaction is far too weak to measure. You will never feel a dark matter particle, you will never see one, but they are there, constantly. A river of invisible mass flowing through the solar system, through the galaxy, holding everything together. The universe runs on things we cannot see, dark matter, dark energy, forces and particles that do not interact with light, that leave no direct trace, but shape everything around us. And that is just the large-scale structure. When you zoom in, when you go smaller than atoms, smaller than protons, down to the scale where quantum mechanics takes over, you find another set of forces, powerful forces. Forces that hold the nucleus together, that let atoms bond into molecules, that make chemistry possible. Forces that, if you could harness them, release more energy per gram than any chemical reaction, any explosion, anything except a matter-antimatter annihilation, the strong force, the weak force, the electromagnetic force, operating at scales so small that for most of human history we did not even know they existed, but they are there. And they are the reason atoms do not just collapse, the reason matter is stable, the reason you can hold a rock in your hand and it stays solid instead of dissolving into a cloud of particles. If you want to understand what rules the universe, you cannot stop at galaxies and black holes and dark matter. You have to go deeper, down to the level where the universe is not smooth, not continuous, but grainy, quantized, discrete, where particles do not have definite positions until you measure them, where empty space is not empty, but seething with virtual particles popping in and out of existence, where the rules are so strange that even physicists who work with them every day admit they do not really understand what is going on. The quantum realm, the foundation underneath everything, the place where the real power, the power that makes atoms possible, lives. The place where the real power, the power that makes atoms possible, lives. And here is what nobody tells you when they teach you about atoms in school. They show you the cartoon, a little nucleus in the center, electrons orbiting around it like planets around a sun. Neat, simple, completely wrong. Or at least, wrong in every way that matters. Atoms do not look like tiny solar systems. Electrons do not orbit. The nucleus is not a solid ball. And the forces holding it all together are so much stranger and so much more powerful than anything happening at the scale of stars and galaxies that when you finally understand what is going on inside an atom, the fact that matter is stable at all starts to feel like a miracle. There are 4 fundamental forces in the universe, just 4. Everything that happens, every interaction, every motion, every event from the Big Bang to the heat death of the cosmos is governed by one or more of these 4 forces. Gravity, which we have already talked about. Electromagnetism, which holds atoms together and makes chemistry possible. The weak nuclear force, which makes stars shine and atoms decay. And the strong nuclear force, which is the most powerful thing in the known universe. That last one is worth pausing on, because when physicists say the strong force is strong, they are not exaggerating. It is not just a little stronger than the other forces. It is not twice as strong or 10 times as strong. At the distances where it operates, inside the nucleus of an atom, the strong force is roughly 100 times stronger than electromagnetism, 1,000,000 times stronger than the weak force, and 10 to the 38th times stronger than gravity. 10 to the 38th. Gravity is so weak compared to the strong force that it might as well not exist. If the strong force is a hurricane, gravity is a whisper in another room. The reason you do not experience the strong force in daily life is that it only works at incredibly short ranges. It operates over distances measured in femtometers. 1 femtometer is 1 quadrillionth of a meter, roughly the diameter of a proton. Step outside that range and the strong force drops to 0. It does not weaken gradually the way gravity does, it just stops. This is why the strong force does not affect you, why it does not hold buildings together or pull on planets. It only works inside atomic nuclei, but inside that tiny range, it is unimaginably powerful, and it has to be. Because the nucleus of an atom is a deeply unstable place. Take a helium nucleus. 2 protons, 2 neutrons, packed into a space about 1 femtometer across. The protons are both positively charged. Positive charges repel. Electromagnetism says those protons should be pushing each other apart with enormous force. At the distances we are talking about, the electromagnetic repulsion between 2 protons is strong enough that if you could somehow isolate them and let them go, they would fly apart at a significant fraction of the speed of light. And yet, the nucleus holds together. The protons do not fly apart. Something is keeping them there. That something is the strong force. The strong force does not care about electric charge. It does not care whether a particle is positive, negative, or neutral. It just pulls. Anything with the right kind of charge, which physicists call color charge, feels the strong force. Protons have it, neutrons have it, electrons do not, photons do not. Only particles made of quarks experience the strong force. And quarks, the particles that make up protons and neutrons, are bound together by the strong force so tightly that you cannot pull them apart, ever. If you try to separate two quarks, the strong force does not weaken as you pull them farther apart. It gets stronger. The farther you pull, the more energy it takes. Eventually, you pump so much energy into the system that the energy itself converts into mass and creates new quarks. You do not separate the original pair, you just make more quarks. This is called confinement, and it is one of the strangest features of the strong force. Quarks are never found alone, they are always bound into groups. 3 quarks make a proton or a neutron. A quark and an antiquark make a meson. But a single quark by itself, isolated, free, that does not exist. The universe does not allow it. The strong force is mediated by particles called gluons. Gluons are to the strong force what photons are to electromagnetism. When 2 protons interact electromagnetically, they exchange photons. When 2 quarks interact via the strong force, they exchange gluons. But gluons are weirder than photons. Photons do not have electric charge, so they do not interact with each other. 2 beams of light pass through each other without affecting each other at all. Gluons have color charge. They feel the strong force. So when 2 quarks exchange gluons, the gluons themselves interact, exchanging more gluons which interact with each other, and the whole thing turns into a self-reinforcing tangle of force-carrying particles that binds the quarks into a stable structure. This is why protons and neutrons are so incredibly stable. It is not just that the quarks inside them are stuck together. It is that the force holding them together is constantly reinforcing itself, creating a web of interactions so dense and so strong that nothing short of colliding protons at near light speed in a particle accelerator can break it. And that leads to the second nuclear force, the weak force. The name is accurate. It is weak. At the same distance scales, it is about 1,000,000 times weaker than the strong force. The weak force operates over even shorter ranges, about 1,000th of a femtometer. Inside that range, it does something the other forces do not. It changes particles into other particles. It lets a neutron turn into a proton, emitting an electron and an antineutrino in the process. This is beta decay, the most common form of radioactive decay, and it is driven entirely by the weak force. Beta decay is why unstable isotopes eventually break down. A neutron inside a nucleus is not stable on its own. Left alone, outside a nucleus, a free neutron will decay into a proton, an electron, and an antineutrino in about 15 minutes. Inside a nucleus, neutrons can be stable because the strong force holds them in place. But in certain isotopes, where the balance between protons and neutrons is off, a neutron will decay anyway. The weak force allows it. The nucleus releases an electron, which we detect as radiation, and the neutron becomes a proton. The element changes. Carbon becomes nitrogen. Potassium becomes calcium. Lead becomes bismuth. This is alchemy, real alchemy, happening naturally inside unstable atoms all the time. The weak force is also responsible for nuclear fusion in stars, not directly. The strong force is what ultimately binds the nuclei together. But fusion in the core of a star like the Sun begins with a process where 2 protons collide and one of them converts into a neutron via the weak force, releasing a positron and a neutrino. That conversion is the bottleneck. It is incredibly slow. The probability of a given proton in the Sun's core undergoing that interaction in any given second is absurdly low. but the Sun has so many protons and they are colliding so often that statistically it happens enough to sustain fusion. If the weak force were stronger, stars would burn through their fuel in millions of years instead of billions. If it were weaker, fusion might not happen at all. The Sun would never have lit up. Life would never have begun. The weak force, despite its name, is essential. The weak force is mediated by three particles, the W+, the W-, and the Z boson. These are heavy particles, about 80 to 90 times the mass of a proton. That mass is why the weak force has such a short range. The more massive the force-carrying particle, the shorter the distance it can travel before its energy runs out. Photons have no mass, so electromagnetism has infinite range. Gluons are massless too, but they interact with each other, which effectively confines them. W and Z bosons are massive, so the weak force drops off extremely quickly. But within that tiny range, the weak force does things no other force can. It violates symmetries. It allows particles to change flavor. It is responsible for the fact that matter exists at all. In the first moments after the Big Bang, when the universe was a hot soup of particles and antiparticles annihilating each other, a tiny asymmetry driven by the weak force led to slightly more matter than antimatter, one extra matter particle for every billion matter-antimatter pairs. When the annihilation was over, that leftover matter became everything. Every atom in the universe, every star, every planet, every person. The weak force is why there is something rather than nothing. Then there is electromagnetism, the force that holds your body together, the force that makes chemistry possible, the force responsible for light, for electricity, for the structure of atoms, for the fact that solid objects are solid. Electromagnetism is everywhere. It is the only force, other than gravity, that you experience directly in everyday life. And unlike gravity, which is always attractive, electromagnetism can push or pull depending on the charges involved. Opposite charges attract, like charges repel. That simple rule is responsible for almost everything that happens at the scale of atoms and molecules. An atom is mostly empty space. If you scaled up a hydrogen atom so that the nucleus was the size of a marble, the electron would be orbiting about half a kilometer away. The space in between is not filled with anything. No air, no ether, just fields, electromagnetic fields. The electron is bound to the nucleus by the electromagnetic attraction between its negative charge and the proton's positive charge. The electron does not orbit in the classical sense. It does not follow a defined path. Quantum mechanics says the electron exists in a cloud of probability, a region around the nucleus where it is most likely to be found. That cloud is called an orbital, and its shape and size are determined entirely by the electromagnetic force and the rules of quantum mechanics. When atoms bond together to form molecules, electromagnetism is doing the work. Electrons from one atom interact with the nucleus of another. Shared electrons, transferred electrons. The details vary depending on the type of bond, but the force is always electromagnetic. Chemistry is applied electromagnetism. Every reaction, every bond formed or broken, every molecule synthesized in a lab or inside a living cell happens because electromagnetic forces between charged particles allow atoms to stick together in specific configurations. Light is electromagnetism. An oscillating electric field creates an oscillating magnetic field, which creates an oscillating electric field, and the wave propagates through space at the speed of light. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. All of them are electromagnetic radiation, differing only in frequency. The light you are seeing right now, The light reflecting off this screen or this page is made of photons, tiny massless packets of electromagnetic energy, emitted when electrons in atoms drop from higher energy levels to lower ones. Every time an electron changes energy, it emits or absorbs a photon. That is how the sun produces light. Electrons in the atoms of the sun's outer layers are constantly being excited by the heat from the core, jumping to higher energy levels and then dropping back down, releasing photons as they fall. Those photons travel through space for 8 minutes, pass through Earth's atmosphere, enter your eye, and trigger a chemical reaction in the cells of your retina. Vision is electromagnetic, so is touch. When you press your hand against a table, you are not actually touching it. The electrons in the outermost layer of atoms in your skin are being repelled by the electrons in the outermost layer of atoms in the table. Electromagnetic repulsion. The closer the atoms get, the stronger the repulsion. You feel that repulsion as solidity, as resistance, but your hand never makes contact with the table in the literal sense. The atoms never touch. There is always a gap, filled with electromagnetic fields pushing back. Solid matter is solid because electromagnetism refuses to let atoms overlap. The electromagnetic force is mediated by photons. When two charged particles interact, they exchange virtual photons. These are not the photons you see as light. They are fluctuations in the electromagnetic field that exist for such a short time that they do not violate the laws of physics, even though they seem to. Virtual photons pop into existence, carry the force between two charges, and disappear. This happens constantly, everywhere. Right now, trillions of virtual photons are being exchanged between the particles in your body. You do not see them, you do not feel them, but they are there, carrying the electromagnetic force that keeps your atoms bound together. Gravity, the fourth fundamental force, is the weakest by far. We talked about that. It is so weak compared to the others that it barely registers at the quantum scale. A single electron interacts with a single proton electromagnetically with a force about 10 to the 39th times stronger than their gravitational attraction. Gravity only matters when you have enormous amounts of mass, planets, stars, galaxies, black holes. At those scales, gravity dominates because it is always attractive and it adds up. Electromagnetism cancels out over large distances because matter is mostly neutral, equal numbers of positive and negative charges. Gravity does not cancel. Every bit of mass pulls on every other bit. So even though gravity is unimaginably weak at the quantum level, it is the only force that matters at cosmic scales. The question that has haunted physicists for the better part of a century is why these four forces exist. Why four and not 3 or 5 or 1? Are they truly separate, or are they different aspects of something deeper? And if they are separate, why do they have such wildly different strengths? Why is the strong force so much stronger than gravity? Why does the weak force operate over such short ranges, while electromagnetism and gravity extend infinitely? These are not just philosophical questions, they are practical ones, because the universe, at a fundamental level, seems to be built from these four forces. Everything that happens is an interaction mediated by one or more of them. If you want to understand how the universe works, you have to understand the forces, and if you want to understand the forces, you have to ask whether they are truly independent or whether they are connected. In the 1960s and 70s, physicists developed a framework called the Standard Model of Particle Physics. It is not a single theory. It is a collection of theories that describe the electromagnetic, weak and strong forces using a common mathematical language. Quantum field theory. The Standard Model organizes all known particles into categories: quarks, which make up protons and neutrons, leptons, which include electrons and neutrinos, force-carrying bosons, which include photons, gluons, W and Z bosons, and the Higgs boson, which gives particles mass. Every particle ever detected in a particle accelerator fits into the Standard Model. The predictions it makes have been tested over and over, and they work absurdly well. The Standard Model is one of the most successful theories in the history of science, but it is incomplete. It does not include gravity. General relativity describes gravity beautifully at large scales, but it is not a quantum theory. It does not fit into the framework of the Standard Model. Every attempt to build a quantum theory of gravity has run into problems. The equations produce infinities. The predictions break down at the Planck scale, the smallest scale where the concepts of space and time still make sense. And the Standard Model cannot explain dark matter. It cannot explain dark energy. It cannot explain why the forces have the strengths they do. It works, but it is not the final answer. Physicists have known for decades that the weak force and electromagnetism are connected. In the 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that at high enough energies, the electromagnetic and weak forces merge into a single force called the electro-weak force. At low energies, the energies we experience in everyday life, the two forces behave differently. Electromagnetism is mediated by massless photons. The weak force is mediated by massive W and Z bosons. But at energies above about 100 GeV, roughly the mass of the W and Z bosons, the distinction disappears. The forces unify. This was not just a mathematical trick. It was confirmed experimentally at particle accelerators in the 1980s. The electro-weak unification is real. That discovery raised the obvious question: if the weak and electromagnetic forces unify, what about the strong force? Is there a higher energy scale where all three forces merge? And if so, what about gravity? Could all four forces be aspects of a single unified force that existed in the first moments after the Big Bang and then split apart as the universe cooled? That is the dream, a theory of everything. A single equation or set of equations that describes all the forces and all the particles in a single unified framework. A theory that explains not just what the forces do, but why they exist and why they have the properties they do. Grand unified theories, or GUTS, try to unify the strong, weak, and electromagnetic forces. They predict that at energies around 10 to the 15 or 10 to the 16 GeV, far higher than anything we can produce in a particle accelerator, the three forces merge into one. GUTS make testable predictions. They predict that protons should decay, though very slowly, with a half-life longer than the current age of the universe. Experiments have been searching for proton decay for decades. So far, nothing. Either protons are even more stable than the simplest GUTS predict, or the theory needs adjustment. String theory goes further. It tries to include gravity. The idea is that particles are not point-like objects, but tiny vibrating strings. Different vibrations correspond to different particles. A string vibrating one way is an electron, vibrating another way, a photon, another way, a graviton, the hypothetical particle that mediates gravity. String theory naturally includes gravity in the quantum framework because gravitons are just another vibration mode. The problem is that string theory requires extra dimensions, not just the 3 spatial dimensions we experience, but 6 or 7 more, curled up so small that we cannot detect them. And string theory makes very few testable predictions at energies we can reach. It is elegant. It is mathematically beautiful, but it is not clear whether it describes reality or whether it is just an interesting mathematical structure. Loop quantum gravity takes a different approach. Instead of starting with particles, it starts with spacetime itself. The idea is that spacetime is not smooth and continuous, but made of discrete chunks, tiny loops of space woven together into a fabric. Gravity emerges from the geometry of that fabric. Loop quantum gravity does not require extra dimensions, it does not need strings, but it also does not unify the forces. It is a quantum theory of gravity, not a theory of everything. The truth is, we do not know how to unify the forces. We have pieces, we have hints, we have mathematical frameworks that look promising, but we do not have a confirmed theory. We do not have experimental data from the energy scales where unification is supposed to happen. Those energies are so high that even our most powerful particle accelerators cannot come close. The Large Hadron Collider, the biggest machine humanity has ever built, reaches energies of about 14 TeV. Grand unification energies are 1 trillion times higher. To test those theories directly, we would need a particle accelerator the size of the solar system. We are not building that anytime soon. But here is the thing. We know unification happened. The universe started hot. In the first moments after the Big Bang, the energy was so high that all the forces were unified. As the universe expanded and cooled, the forces split apart. First gravity separated, then the strong force. Then the electro-weak force split into electromagnetism and the weak force. Each split changed the rules. Each split created new possibilities. Without those splits, without the forces separating and taking on different properties, the universe could not have formed the structures we see today. No atoms, no stars, no galaxies, no life. The forces, in their current separated state, are what make complexity possible. The power within the atom is real. Nuclear fusion releases energy by converting mass into energy via Einstein's equation. The strong force binds quarks and nuclei with a grip so tight that breaking it releases more energy per gram than any chemical reaction. The weak force allows particles to transform, enabling the fusion that powers stars and the decay that makes elements. Electromagnetism holds atoms together, makes molecules possible, and gives us light. These forces are not abstract. They are not theoretical. They are operating right now, in every atom in your body, in every photon hitting your eye, in every nucleus holding itself together against the electromagnetic repulsion trying to tear it apart. And yet, as powerful as these forces are, as essential as they are to the structure of matter, they are still incomplete. They are pieces of a puzzle we have not yet solved. Gravity does not fit. Dark matter does not fit. Dark energy does not fit. The standard model works within its domain, but that domain is not the whole universe. There is more, something deeper. Something that connects the forces, that explains why they exist, that unifies the quantum realm with the curved spacetime of general relativity. Physicists have been searching for that connection for decades. They call it the theory of everything, and the search is not over. It is just beginning. And the search is not over. It is just beginning. But here is where the whole project hits a wall that has been standing for more than a century, a wall that thousands of the smartest people on Earth have been throwing themselves against, again and again, with no confirmed breakthrough. Because everything we have talked about so far, every force, every particle, every interaction, fits into one of two frameworks: general relativity for gravity and spacetime, quantum mechanics for everything else. And those two frameworks do not talk to each other. They are not just different languages, they are different realities. And when you try to force them together, when you try to describe a situation where both gravity and quantum mechanics matter, the mathematics breaks, the predictions become nonsense, the equations produce infinities, and physicists are left staring at a universe that clearly works but refuses to explain itself in a way that makes sense on paper. This is the central problem of modern physics. The question that keeps theoretical physicists awake at night. How do you unify general relativity and quantum mechanics? How do you build a theory that describes both the curvature of spacetime around a black hole and the behavior of particles inside an atom? How do you create a single framework that works everywhere, from the Planck scale to the scale of galaxy clusters, from the first moment after the Big Bang to the heat death of the universe? That unified framework, if it exists, is what physicists call a theory of everything. And despite decades of effort, despite brilliant minds and elegant mathematics, we do not have one. Not yet. General relativity is a theory of smooth spacetime. It describes gravity not as a force, but as the curvature of a four-dimensional fabric. Mass and energy tell spacetime how to bend. Curved spacetime tells matter how to move. The equations are deterministic. If you know the distribution of mass and energy at one moment, you can predict what spacetime will look like at any other moment. There is no randomness, no uncertainty. The universe, according to general relativity, is a clockwork. Beautiful, predictable, continuous. Quantum mechanics is the opposite. It is a theory of probabilities. Particles do not have definite positions or velocities until you measure them. They exist in superpositions, spread out over multiple possible states at once. The act of measurement collapses the superposition, forcing the particle to pick one state. Before the measurement, the particle is not in a hidden definite state that you just do not know. It is genuinely in all the possible states simultaneously. This is not philosophy. This is how the universe works at small scales. Electrons do not orbit nuclei in defined paths. They exist in clouds of probability. Photons do not travel along single trajectories. They take all possible paths at once. Quantum mechanics is strange, uncertain, and deeply uncomfortable if you are used to thinking about the world as something solid and predictable. For most situations, you only need one framework or the other. If you are calculating the orbit of a planet, general relativity works fine. Quantum effects are negligible. If you are calculating the energy levels of an electron in an atom, quantum mechanics works fine. Gravity is too weak to matter. The two theories operate in separate domains, and for a long time, that was enough. But there are places in the universe where both domains overlap, where gravity is so strong and distances are so small that you cannot ignore either framework. The center of a black hole. The first fraction of a second after the Big Bang. Anywhere spacetime curves so sharply that quantum effects become important. In those places, you need both theories, and when you try to use both at once, everything falls apart. The problem shows up most clearly when you try to quantize gravity. Quantizing a force means treating it the way quantum mechanics treats the other forces. Electromagnetism is mediated by photons. The strong force is mediated by gluons. The weak force is mediated by W and Z bosons. So gravity should be mediated by a particle too, a graviton, a massless spin-2 particle that carries the gravitational force. That part is fine. The mathematics of gravitons works at low energies. You can write down a quantum field theory of gravity, and for weak gravitational fields, the predictions match general relativity. The trouble starts when you try to go to higher energies, when you calculate what happens when gravitons interact with each other. The equations blow up. You get infinities. Not infinities that can be removed with clever mathematical tricks, the way they can in quantum electrodynamics. Real, unmanageable infinities that make the theory useless. This is not just an inconvenience, it is a sign that something fundamental is missing. General relativity and quantum mechanics are both extraordinarily successful theories. They have been tested in every conceivable way, and they work. But they cannot both be the final answer because they give different predictions in extreme conditions, and there is no consistent way to merge them. One or both of them has to be incomplete, not wrong, incomplete. An approximation that works within a certain range but breaks down when pushed too far. Physicists have known this for decades. The hope has always been that at some deeper level there is a unified theory. A framework that includes both general relativity and quantum mechanics as special cases. A theory that reduces to general relativity when gravity is strong and quantum effects are weak. A theory that reduces to quantum mechanics when quantum effects are strong and gravity is weak. And a theory that gives clear, finite, testable predictions when both are strong. A theory of everything. Grand unified theories were an early attempt, but they do not go far enough. Guts unify the strong, weak, and electromagnetic forces. They show that at very high energies, around 10 to the 15th or 10 to the 16th giga-electron volts, those three forces merge into a single force. The particles that mediate them become interchangeable. The distinctions between quarks and leptons blur. At those energies, the universe would have looked very different, simpler, more symmetric. But guts do not include gravity. They are not theories of everything. They are theories of almost everything. 3 out of 4 forces. Gravity is still separate, still described by general relativity, still incompatible with the quantum framework. Guts are an important step, but they do not solve the central problem. String theory goes further. It is the best-known candidate for a true theory of everything, and it has been the dominant framework in theoretical physics for more than 3 decades. The core idea is simple, almost absurdly so. What if particles are not point-like objects? What if they are not zero-dimensional dots, but one-dimensional strings? Tiny loops or segments of vibrating energy, far too small to see even with the most powerful microscopes, but extended nonetheless. Different vibrations of the string correspond to different particles. A string vibrating one way looks like an electron, vibrating another way, a photon, another way, a quark, another way, a graviton. This idea is not new. String theory has roots going back to the late 1960s, when physicists were trying to understand the strong force. The theory was sidelined for years, considered a mathematical curiosity with no clear connection to reality. Then, in the mid-1980s, something changed. Physicists realized that string theory naturally includes gravity. You do not have to force gravitons into the framework. They emerge automatically. A string vibrating in a particular way behaves exactly like a graviton, the particle that mediates gravity in a quantum theory. And when you calculate interactions between gravitons in string theory, the infinities that plague other approaches disappear. The mathematics is finite, the predictions make sense. For the first time, physicists had a quantum theory of gravity that actually worked. String theory does more than just unify gravity with the other forces. It unifies all the particles. In the standard model, particles are treated as separate entities. Electrons, quarks, photons, gluons, all distinct. In string theory, they are all the same thing. Different vibrations of the same underlying string. The diversity of the particle zoo is not fundamental. It is just a consequence of how strings can vibrate. This is deeply elegant. Instead of asking why the universe has so many different kinds of particles, string theory suggests there is really only one kind of thing: strings. Everything else is just music. But string theory comes with a cost. A strange, uncomfortable cost that has bothered physicists since the beginning. The mathematics only works if spacetime has more than 4 dimensions, not just the 3 spatial dimensions we experience, plus time. String theory requires 10 dimensions, or 11, depending on which version you are working with. 6 or 7 extra dimensions beyond the 4 we know. Where are they? Why do we not see them? The usual answer is that the extra dimensions are compactified, curled up so small that they are invisible. Imagine a garden hose. From a distance, it looks one-dimensional, a line. But if you zoom in, you see that the surface of the hose is actually 2-dimensional. There is a length, which you can see from far away, and a circumference, which you can only see up close. The extra dimensions in string theory are like that circumference. They exist, but they are curled up at scales far smaller than anything we can probe. Smaller than atoms, smaller than protons, smaller than quarks. Down near the Planck length, about 10 to the minus 35 meters, where quantum gravity effects become important. If the extra dimensions are that small, we will never see them directly, but their existence would have consequences. The way the extra dimensions are curled up, their shape and size, determines the properties of particles in the 4-dimensional spacetime we experience, the masses of particles, the strengths of forces, the values of constants. In string theory, all of those properties are not arbitrary. They are determined by the geometry of the extra dimensions. This is one of the theory's most attractive features. It offers an explanation for why the universe has the properties it does, not because those properties were dialed in by hand, but because the geometry of the hidden dimensions forces them to be that way. The problem is that there are many ways to curl up the extra dimensions, many different shapes they could take. And each shape gives a different set of particle properties, different masses, different forces, different physics. Estimates suggest there could be 10 to the 500 different ways to compactify the extra dimensions, 10 to the 500 different versions of string theory, each one mathematically consistent, each one giving a different universe. This is called the landscape problem, and it is one of the biggest criticisms of string theory. If the theory can predict almost anything, depending on which version you pick, then it does not really predict anything. It loses its power as a scientific theory. String theory also has another problem. It is extraordinarily difficult to test. The energy scales where string effects become important are far, far beyond anything we can reach in a particle accelerator. The Large Hadron Collider, the most powerful machine ever built, reaches energies of about 14 tera-electron volts. String theory becomes relevant at the Planck scale, about 10 to the 19th giga-electron volts. That is 1,000,000 trillion times higher. Building an accelerator that could probe those energies directly would require a machine larger than the solar system. We are not doing that. So string theory makes very few testable predictions at energies we can actually explore. It is mathematically beautiful. It solves the problem of infinities in quantum gravity. It unifies all the forces and particles. But it is not clear whether it describes the universe we live in, or just a universe that could exist mathematically. In the 1990s, string theory evolved. Physicists realized that there were 5 different versions of string theory, each with slightly different properties. For a while, that looked like a problem. If string theory was supposed to be the theory of everything, why were there 5 versions? Then Edward Witten and others showed that the 5 theories were not truly separate. They were different limits of a single deeper theory. A theory that lives in 11 dimensions instead of 10. a theory where the fundamental objects are not just strings, but higher dimensional objects called brains, membranes, sheets of energy that can have multiple dimensions. A zero brain is a point, a one brain is a string, a two brain is a surface, and so on. This larger framework is called M-theory. The M officially stands for membrane, though Witten has joked that it could stand for magic, mystery, or matrix, depending on taste. M-theory is not a finished theory. It is more like a framework, a set of dualities and relationships that connect the different string theories. Nobody has written down the fundamental equations of M-theory in a complete form, but the framework exists, and it suggests that string theory is part of something bigger, something that includes not just strings but brains of all dimensions, interacting in an 11-dimensional spacetime. If M-theory is correct, the extra dimensions are not just a technical detail. They are central to the structure of reality. Our four-dimensional spacetime might be a brain, a four-dimensional sheet embedded in a higher dimensional space. Particles might be strings attached to that brain. Gravity might propagate through the higher dimensional bulk. This is speculative, but it opens up possibilities that sound like science fiction. Parallel brains, other universes existing in dimensions we cannot access. Collisions between brains that could trigger events like the Big Bang. String theory and M-theory are not the only candidates. Loop quantum gravity takes a completely different approach. Instead of starting with particles or strings, it starts with spacetime itself. The idea is that spacetime is not smooth and continuous, but made of discrete chunks, tiny loops of space woven together into a fabric. Gravity emerges from the geometry of that fabric. At large scales, the loops are so small that spacetime looks smooth and general relativity is recovered. At small scales, near the Planck length, the discrete structure becomes important and quantum effects dominate. Loop quantum gravity does not require extra dimensions. It does not need strings or brains. It is a quantum theory of geometry. The downside is that loop quantum gravity does not naturally include the other forces. It is a quantum theory of gravity, not a theory of everything. Unifying it with the standard model is still an open problem. There are other ideas. Causal set theory, which treats spacetime as a collection of discrete events connected by causal relationships. Asymptotic safety, which suggests that quantum gravity might be consistent without needing a more fundamental theory like strings. Emergent gravity, which proposes that spacetime and gravity are not fundamental but emerge from deeper quantum information. Each approach has its strengths and weaknesses. Each has passionate advocates, but none has been confirmed experimentally. We are still guessing. The lack of experimental data is the biggest obstacle. Physics is an experimental science. Theories are tested against observations. If a theory makes a prediction that turns out to be wrong, the theory is discarded or modified. But the energy scales where quantum gravity becomes important are so far beyond what we can reach that direct tests are impossible. We cannot build a collider that reaches the Planck energy. We cannot create a black hole in a lab and watch it evaporate. We cannot go back to the first moment after the Big Bang and take measurements. The universe does not make this easy, so physicists look for indirect tests. They study the cosmic microwave background, searching for subtle patterns that might reveal information about the quantum structure of spacetime in the early universe. They analyze gravitational waves from black hole mergers, looking for tiny deviations from the predictions of general relativity that might hint at quantum corrections. They search for violations of Lorentz symmetry, the principle that the laws of physics are the same in all directions, which some quantum gravity theories predict could break down at small scales. So far, nothing, no confirmed deviation, no smoking gun. The universe keeps its secrets. Stephen Hawking once said that the dream of a theory of everything is not merely to describe the universe, but to explain why it exists. That is the real promise. Not just unifying the forces, not just merging general relativity and quantum mechanics, but understanding why the universe has the structure it does, why there are 4 forces instead of 3 or 5, why the constants have the values they have, why the universe is comprehensible at all. A true theory of everything would answer those questions, or at least it would give us a framework for asking them in a way that makes sense. The fact that we do not have that theory yet does not mean the search is pointless. The process of looking has already taught us an enormous amount. String theory, whether or not it is the final answer, has revolutionized mathematics. It has led to deep insights into the structure of black holes, the nature of entropy, the holographic principle, the idea that all the information in a volume of space can be encoded on its boundary. Loop quantum gravity has forced physicists to rethink what spacetime is at a fundamental level. The search for unification has driven the development of new mathematical tools, new experimental techniques, new ways of thinking about the universe, and the search continues. Right now, at universities and research institutes around the world, physicists are working on this problem. They are writing equations, running simulations, looking for patterns in data, proposing new ideas, testing old ones, arguing over interpretations, making slow, incremental progress. It is not glamorous, it is not fast, but it is happening. And every so often, someone finds a piece that fits, a new insight, a new connection, a new way of looking at the problem that makes things a little clearer. The universe had a beginning, we know that. The Big Bang was not just the start of matter and energy, it was the start of space-time itself. Before the Big Bang, there was no before. Time did not exist. Space did not exist. Everything that is, everything that has ever been, came from that first moment. And in that first moment, the universe was unimaginably hot and dense. The 4 forces were not separate. They were unified. Gravity, electromagnetism, the strong force, the weak force, all merged into a single superforce. As the universe expanded and cooled, the forces split apart. First gravity, then the strong force, then the electro-weak force, which later split into electromagnetism and the weak force. Each split was a transition, a phase change, like water freezing into ice. And each split shaped the universe in ways that persist today. If we want to understand that first moment, if we want to know what happened in the first fraction of a second after the Big Bang, we need a theory of everything. General relativity breaks down at the singularity. Quantum mechanics cannot describe the entire universe. Only a unified theory can tell us what happened, what the universe looked like when it was smaller than an atom, what the laws of physics were when the temperature was 10 to the 32 Kelvin and the forces were 1, whether the Big Bang was truly the beginning or whether it was a transition from some earlier state, whether our universe is the only universe or one of many. These are not abstract questions, they are questions about the most powerful event that ever occurred, the event that created everything, the explosion that set the initial conditions for every star, every galaxy, every planet, every atom. The Big Bang was not just powerful in the sense of releasing energy, it was powerful in the sense of creating the possibility of energy, of matter, of space-time, of structure, of complexity, of life. If we want to understand what really rules the universe, we have to go back to that moment. We have to look at the echoes, the faint signals still traveling through space, the patterns left behind in the cosmic microwave background, the distribution of galaxies, the abundance of elements, the expansion rate, all of it traces back to those first moments. And those moments, more than any explosion, any force, any object we have talked about, hold the key. Because the power that shapes the universe is not just in the events happening now, it is in the conditions set at the beginning, in the initial state, in the laws that governed the first fraction of a second and have governed everything since. The universe is not random, it is not arbitrary. It has structure, it has rules, and those rules came from somewhere, from some process, some principle, some deeper reality that we are still trying to uncover. A theory of everything would not just unify the forces, it would explain the rules themselves, why they exist, why they take the form they do, why the universe is the way it is and not some other way. We do not have that theory, but we know where to look. In the earliest moments, in the hottest, densest, most extreme conditions the universe has ever known, in the echoes of creation itself, and those echoes are still here. Right now, at this exact moment, there is radiation passing through your body that has been traveling for more than 13 billion years. It is faint, cold, almost perfectly uniform. It is not coming from a star. It is not coming from a galaxy. It is coming from everywhere at once, from the entire sky. This is the cosmic microwave background, the afterglow of the Big Bang, and it is the oldest light in the universe. Every photon in that glow was released when the universe was about 380,000 years old, when atoms first formed and light could finally travel freely through space. Before that, the universe was opaque, a hot fog of particles so dense that photons could not move more than a tiny fraction of a distance before colliding with an electron or a proton. The universe was glowing, unimaginably bright, but that light was trapped, scattered endlessly, unable to escape. Then the universe cooled enough for electrons and protons to combine into hydrogen atoms. The fog cleared, and the light was released all at once in every direction. That light has been traveling ever since, stretched by the expansion of space, redshifted from visible light into microwaves, and it is still here. A faint whisper at about 2.7 Kelvin, just a few degrees above absolute zero, filling the entire observable universe. That whisper is the most important signal in cosmology. It is direct evidence that the universe had a beginning, that it was once unimaginably hot and dense, that it has been expanding and cooling for nearly 14 billion years. And when you map that signal across the entire sky, when you measure its temperature in every direction with extraordinary precision, you see something remarkable. The temperature is almost perfectly uniform, almost, but not quite. There are tiny fluctuations, variations of about 1 part in 100,000, regions that are slightly hotter, regions that are slightly colder. Those fluctuations are not noise, they are not random, they are the seeds of everything. Every galaxy, every star, every planet, every structure in the universe today grew from those tiny ripples in the temperature of the early universe. Gravity amplified them over billions of years, turning small overdense regions into galaxy clusters and small underdense regions into voids. The pattern you see in the cosmic microwave background is the blueprint, the initial conditions, the starting point for all the structure we observe. But the cosmic microwave background is not the beginning. It is a snapshot taken 380,000 years after the beginning. An important snapshot, but not the first frame. If you want to understand the true origin, if you want to see where the power came from, you have to rewind further, past the moment when atoms formed, past the moment when nuclei formed, all the way back to the first fraction of a second after the Big Bang. That is where the story gets strange. The universe began with space and time themselves. There was no before, not in any meaningful sense. Time did not exist before the Big Bang, because time is part of the universe, part of the fabric of space-time that general relativity describes. Asking what happened before the Big Bang is like asking what is north of the North Pole. The question does not make sense. The direction does not exist. The universe is not something that exploded into a pre-existing empty space. Space itself was created in the expansion. The Big Bang was not an explosion in space. It was an explosion of space. Every point in the universe, every location you can name, was once in the same place, not clustered together in some distant corner. Actually, the same place, infinite density, infinite temperature. At least, that is what the equations of general relativity say. And then, for reasons we still do not fully understand, space began expanding, rapidly, violently, carrying matter and energy with it. In the first moments, the universe was far too hot for anything we would recognize as matter to exist. No atoms, no nuclei, no protons or neutrons, just a searingly hot soup of fundamental particles and radiation. Quarks and gluons, the building blocks of protons and neutrons, were not bound together yet. They moved freely in what physicists call a quark-gluon plasma. Photons, the particles of light, were constantly colliding with electrons, scattering in every direction. The universe was opaque, glowing, impossibly dense. The temperature was trillions of degrees. Conditions so extreme that we cannot replicate them in any laboratory. The closest we have come is in particle accelerators like the Large Hadron Collider, where protons are smashed together at near light speed, briefly recreating a tiny droplet of quark-gluon plasma for a fraction of a second before it dissipates. Those experiments give us a glimpse, a small window into the conditions of the early universe. But they are just a glimpse. The real thing was everywhere, filling all of space, sustained not for a microsecond, but for the first few microseconds of cosmic history. As the universe expanded, it cooled, and as it cooled, particles began to combine. Quarks bound together to form protons and neutrons. This happened about 1 microsecond after the Big Bang, 1/1,000,000th of a second. Before that moment, quarks were free. After that moment, they were confined inside protons and neutrons, held together by the strong force, locked into the particles that would eventually form every atomic nucleus in the universe. That transition is called quark confinement, and it is one of the most important phase changes in cosmic history. It set the stage for everything that came next. The universe kept expanding, kept cooling. By the time the universe was about 1 second old, the temperature had dropped to about 10 billion degrees, still unimaginably hot by any human standard, but cool enough that something new could happen. Protons and neutrons, now stable, could start sticking together. Not into atoms yet, into nuclei. This is Big Bang nucleosynthesis, and it lasted for only a few minutes. A brief window between about 1 second and 20 minutes after the Big Bang, when the temperature was in the sweet spot where nuclear fusion could occur. Too hot, and the nuclei would be ripped apart by radiation as soon as they formed. Too cool, and the particles would not have enough energy to overcome the electromagnetic repulsion and fuse in the first place. During those few minutes, the universe built the first elements, mostly hydrogen, which is just a single proton, but also helium, which is 2 protons and 2 neutrons bound together, a small amount of deuterium, hydrogen with an extra neutron, trace amounts of lithium, and that was it. No carbon, no oxygen, no iron. Those heavier elements would not be created until the first stars formed, hundreds of millions of years later, and began fusing lighter elements into heavier ones in their cores. but the helium created in Big Bang nuclear synthesis is still here. About 25% of the ordinary matter in the universe by mass is helium. Not helium created in stars, helium created in the first few minutes after the Big Bang. We can measure the helium abundance in old stars, in gas clouds, in distant galaxies, and it matches the predictions of nuclear synthesis almost perfectly. That match is one of the strongest pieces of evidence for the Big Bang model. The universe had to go through a hot, dense phase to produce that much helium. No other process gets the numbers right. After nuclear synthesis ended, the universe had nuclei, but no atoms. Electrons were still free, zipping around, colliding with photons, keeping the universe opaque. For the next few 100,000 years, not much happened. The universe expanded, cooled, thinned out. It was a long, quiet waiting period. Then, at about 380,000 years, the temperature dropped below about 3,000 Kelvin, cool enough for electrons to combine with nuclei and form neutral atoms. Hydrogen atoms, helium atoms. This is called recombination, though that name is misleading because the electrons and nuclei had never been combined before. The moment recombination happened, the universe became transparent. Photons stopped scattering off free electrons. They could suddenly travel freely through space. The light that was released at that moment is the cosmic microwave background, the oldest light in the universe, and it has been traveling ever since, stretched by the expansion of space from visible light into microwaves, cooling from 3000 Kelvin to 2.7 Kelvin, but still here, still detectable, still carrying information about the state of the universe when it was less than 500,000 years old. The cosmic microwave background was discovered by accident in 1965. Two radio astronomers, Arno Penzias and Robert Wilson, were testing a sensitive antenna at Bell Labs in New Jersey. They were trying to map radio signals from the Milky Way. But no matter where they pointed the antenna, they picked up a persistent hiss, a faint background noise that would not go away. They checked the equipment. They cleaned the antenna, removing what they politely called a white dielectric material, which was actually pigeon droppings, in case that was causing the problem. The signal remained. It was coming from every direction in the sky, uniform, faint, consistent. They did not know what it was. Then they heard about theoretical work by physicists Robert Dicke and Jim Peebles at Princeton, who had predicted that if the Big Bang model was correct, there should be leftover radiation from the early universe, cooled by expansion to just a few degrees above absolute zero. Penzias and Wilson had found it. The signal they were detecting was not noise, it was the afterglow of creation. They won the Nobel Prize in Physics in 1978 for the discovery. Since then, the cosmic microwave background has been mapped in extraordinary detail. First by the COBE satellite in the early 1990s, which confirmed that the spectrum of the radiation matched the predictions of Big Bang theory almost perfectly. Then by the WMAP satellite in the 2000s, which mapped the tiny temperature fluctuations across the sky with much higher resolution. And most recently by the Planck satellite, which produced the most detailed map of the cosmic microwave background ever made. The data from these missions has been analyzed in every conceivable way. The results have been used to measure the age of the universe, the density of matter and dark matter, the amount of dark energy, the geometry of spacetime, the initial conditions that led to galaxy formation. The cosmic microwave background is not just evidence for the Big Bang. It is a data goldmine, a fossil record of the universe's infancy, and it keeps giving answers. One of the most important things the cosmic microwave background tells us is that the early universe was almost perfectly smooth. The temperature fluctuations are only about 1 part in 100,000. That uniformity is a problem. Or at least, it was a problem until physicists figured out what caused it. If the universe expanded at the rate predicted by standard Big Bang models, with no modifications, regions on opposite sides of the sky should never have been in contact with each other. They were too far apart. Light would not have had time to travel between them. And yet, they have almost exactly the same temperature. How do you explain that? How do two regions that have never communicated, that have never exchanged light or heat or information, end up at the same temperature? That is the horizon problem, and for a long time it was one of the biggest puzzles in cosmology. The solution is inflation. A brief period, starting about 10 to the minus 36 seconds after the Big Bang, and lasting until about 10 to the minus 32 seconds, during which the universe expanded exponentially, not just fast, exponentially fast. In a tiny fraction of a second, the universe grew by a factor of at least 10 to the 26, possibly much more. That expansion was so rapid that regions of space that had been in contact, that had equalized their temperature, were suddenly on opposite sides of the observable universe. The uniformity we see in the cosmic microwave background is not a coincidence. It is a consequence of inflation. The entire observable universe, all the regions we can see, came from a patch of space smaller than an atom. That patch was uniform because it was small enough for light and heat to smooth things out. Then inflation stretched it to cosmic scales. Inflation also explains where the fluctuations came from. The tiny ripples in the cosmic microwave background, the 1 part in 100,000 variations, are quantum fluctuations blown up to cosmic scales. In the very early universe, space itself was subject to quantum uncertainty. Tiny random fluctuations in energy density, the kind predicted by quantum mechanics, were stretched by inflation from subatomic scales to scales larger than galaxies. Those quantum ripples became the seeds of structure. Gravity amplified them over billions of years, turning slight overdensities into galaxy clusters and slight underdensities into voids. The cosmic web, the largest structure in the universe, traces its origin back to quantum fluctuations in the first fraction of a second after the Big Bang. That is one of the most profound connections in physics. The smallest scales and the largest scales, linked by the process of inflation. Inflation is not just an idea invented to solve problems, it makes predictions. One of the key predictions is that the universe should be flat. Not flat in the sense of two-dimensional, but flat in the sense that the geometry of space should follow the rules of Euclidean geometry. Parallel lines should stay parallel. The angles of a triangle should add up to 180 degrees. If inflation happened, the universe should be flat to within an extraordinarily small margin of error. And when the cosmic microwave background was measured with high precision, that is exactly what was found. The universe is flat. The measurements from Planck are consistent with a perfectly flat geometry to better than 1%. That is strong evidence for inflation. But inflation raises new questions. What drove it? What caused space to expand so rapidly? The leading idea is that inflation was powered by a field, similar to the Higgs field, called the inflaton. The inflaton field had a very high energy density in the early universe. That energy density acted like a cosmological constant, a kind of vacuum energy that pushed space apart. As the inflaton field rolled down to a lower energy state, it released its energy, reheating the universe and filling it with particles and radiation. That reheating phase is when the hot, dense conditions we associate with the traditional Big Bang model actually began. Inflation happened first. The Big Bang, in a sense, came after. We do not know what the inflaton field is. We do not know if it is a single field or multiple fields. We do not have a confirmed detection of it, but inflation solves so many problems and makes so many correct predictions that most cosmologists accept it as part of the standard model of cosmology. It is the best explanation we have for why the universe looks the way it does, why it is flat, why it is uniform, why it has the tiny fluctuations that led to galaxies. Inflation is the framework that ties the quantum realm to the cosmic web, the bridge between the smallest and largest scales, and inflation is powerful, not in the sense of releasing energy, though it did that too. Powerful in the sense of shaping everything. The universe today, with its hundreds of billions of galaxies, its stars and planets and black holes, its structure and complexity, all traces back to those first moments, to the quantum fluctuations, to the exponential expansion, to the release of energy that reheated the universe and set the stage for nuclear synthesis, recombination, and galaxy formation. Everything we see, everything we measure, everything we are, came from that initial burst, not an explosion in the traditional sense, an expansion, a stretching of space itself, driven by processes we are still trying to understand. The Big Bang was not just the most powerful event in history. It was the only event that created history. Before it, there was no time, no space, no particles, no forces, no structure, no possibility. Everything came from that first moment. The energy density at the Planck time, the earliest moment we can meaningfully describe, was so high that the numbers stop making intuitive sense. Estimates suggest the energy density of the universe at 10 to the minus 43 seconds after the Big Bang was about 10 to the 96 joules per cubic meter. For comparison, the core of the Sun has an energy density of about 10 to the 15 joules per cubic meter. The early universe was incomprehensibly more energetic than anything we can create or observe today. And all of that energy, all of that potential, was packed into a region smaller than the nucleus of an atom. As the universe expanded, that energy was converted into matter and radiation, quarks, gluons, electrons, photons, neutrinos, the fundamental particles that make up everything. The forces that govern their interactions were unified at first, but they split apart as the universe cooled. First gravity separated, then the strong force, then the electromagnetic and weak forces. Each split was a transition, a phase change that reshaped the rules. By the time the universe was a few minutes old, the forces were separate, the particles were stable, and the first nuclei had formed. The stage was set for stars and galaxies to eventually emerge. The echoes of that creation are everywhere, in the cosmic microwave background, in the abundance of helium, in the large-scale structure of the universe, in the expansion rate, in the flatness of space, in the uniformity of the sky. Every measurement we make, every observation we take, points back to those first moments. The universe had a beginning. It was hot, it was dense, it expanded, it cooled, and over nearly 14 billion years, it became the place we see today. A place with stars and planets and galaxies, a place with chemistry and complexity and life, a place where conscious beings can look up at the sky, detect the faint glow of the cosmic microwave background, and trace the history of everything back to a moment of unimaginable power. And here is what makes the Big Bang different from every other powerful event we have talked about. A hypernova releases energy for a few seconds, and then it is over. A gamma-ray burst lasts minutes and fades. A quasar shines for millions of years and then goes quiet. A black hole can last trillions of years, but eventually, even black holes evaporate via Hawking radiation. Everything ends. But the Big Bang did not just release energy. It set the initial conditions. It created the framework. It wrote the rules. The power of the Big Bang is not just in what it did, it is in what it made possible. Every force, every particle, every structure, every star that will ever shine, every planet that will ever form, every thought that will ever occur, all of it traces back to that first moment, not because the Big Bang caused everything directly, but because it created the possibility of everything. That is the deepest kind of power, not the power to destroy or reshape or move, the power to create the conditions for existence itself, to go from nothing or from something we cannot describe to a universe with structure, with laws, with potential. The Big Bang was not an explosion in the sense of violence, it was an explosion in the sense of possibility, and that explosion is still happening. The universe is still expanding. Space is still stretching. The echoes are still traveling through the cosmos, carrying information about where we came from and where we are going. And if we want to understand what really rules the universe, we cannot stop at forces or particles or explosions. We have to ask what power is, what it means. Whether the most powerful thing is the event that releases the most energy, or the event that creates the conditions for energy to exist at all. Because in the end, power is not just about scale or intensity or destruction. It is about influence, about shaping outcomes, about creating possibilities. And by that measure, the Big Bang is the most powerful thing that ever happened. Not because it was violent, but because it was first. Because in the end, power is not just about scale or intensity or destruction. It is about influence, about shaping outcomes, about creating possibilities, and by that measure, the Big Bang is the most powerful thing that ever happened. Not because it was violent, but because it was first. But that raises a question we have been circling around for this entire video. What does power actually mean? Because we started with a hypernova, a stellar explosion that can briefly outshine an entire galaxy, a billion-degree fireball tearing a star apart from the inside and scattering its guts across light years of space. That feels powerful. That looks powerful. The energy release is staggering, the violence is absolute, and the timescale is immediate. 10 seconds of fury that releases more energy than our sun will produce in its entire 10 billion-year lifetime. If you were trying to define cosmic power by the standards humans use for everything else, raw energy output per unit time, a hypernova would be near the top of the list. It is an explosion. It destroys. It reshapes. It leaves a mark. Then we moved to gamma-ray bursts. Even more concentrated, even more violent, jets of matter and radiation screaming outward at nearly the speed of light, beamed across billions of light years, so bright that one happened to be visible to the naked eye from a distance of 7.5 billion light years. For a few seconds, a gamma-ray burst can be the brightest object in the universe, not in a galaxy, in the universe. If you were ranking cosmic phenomena by peak luminosity, gamma-ray bursts would win. They are the flashbulbs of the cosmos, brief, brilliant, and gone. Quasars last longer, millions of years instead of seconds. Supermassive black holes at the centers of galaxies, feeding so aggressively that they outshine every star in the galaxy around them. The radiation pouring out of a quasar is strong enough to push gas out of the galaxy entirely, shutting down star formation, regulating how galaxies grow. A quasar does not just shine, it shapes, it controls, it determines whether a galaxy becomes a star factory or a barren wasteland. That feels like power. Not the power of a single event, but the power of sustained influence. The power to alter the destiny of an entire galaxy over millions of years. Black holes are more patient. They do not flare. They do not burst. They just exist. and anything that falls too close never comes back. Black holes bend space-time so severely that they create regions where escape is not difficult. It is impossible, not because you lack the technology or the fuel, because the universe does not allow it. Once you cross the event horizon, every path leads inward. You are not moving toward the singularity. The singularity is in your future, as inevitable as next Tuesday. That is a different kind of power, not the power to destroy, though black holes do that too, the power to rewrite the rules, to make certain outcomes unavoidable. Dark matter holds galaxies together. It does not glow, it does not radiate. It does not do anything except exist and exert gravity, and that is enough. Without dark matter, galaxies would not exist. The visible matter, all the stars and gas we can see, does not have enough mass to hold a galaxy together against the speed at which stars are orbiting. Dark matter provides the scaffolding, the framework, the invisible structure that makes galaxies possible in the first place. It is not dramatic, it is not violent, but it is essential. Galaxies are not held together by stars, they are held together by dark matter, by something we cannot see, cannot touch, and do not fully understand. Dark energy pushes the universe apart. It does not cluster, it does not form structures. It just fills space, exerting a constant outward pressure that accelerates the expansion of the universe. Galaxies that are not gravitationally bound to each other are moving apart faster every year, carried by the expansion of space itself. Dark energy is the majority of the universe, 68% of everything that exists, and it is winning. Gravity built the galaxies, but dark energy is pulling them apart. In the far future, when the last stars have burned out and the black holes have evaporated, dark energy will still be there, pushing, stretching, driving the universe toward a cold, empty, endless expansion. That is power. Not the power of an event, but the power of inevitability. The power to determine the ultimate fate of everything. The strong force holds atomic nuclei together. It operates over distances smaller than a proton, but within that range, it is the most powerful force in the universe, 100 times stronger than electromagnetism, 1,000,000 times stronger than the weak force, 10 to the 38th times stronger than gravity. The strong force does not just bind protons and neutrons into nuclei, it makes atoms possible, and without atoms there is no chemistry, no molecules, no complexity, no life. The strong force does not operate on the scale of galaxies or stars. It operates on the scale of femtometers. But every atom in your body, every bond holding your molecules together, every structure that makes you a person instead of a cloud of particles, exists because the strong force works. That is power. Not the power of scale, but the power of foundation. The power to make everything else possible. And the Big Bang, the event that created space-time itself. The moment when the universe went from nothing, or from something we cannot describe, to a state of unimaginable energy density, and then expanded, cooled, and evolved into the structured, complex, law-governed cosmos we see today. The Big Bang was not just an explosion. It was the creation of the possibility of explosion, of energy, of matter, of forces, of structure. Every particle, every force, every law, every event that has happened in the nearly 14 billion years since that moment traces back to the initial conditions set by the Big Bang. That is power. Not the power to destroy or reshape, the power to create the framework within which destruction and reshaping can occur. So what is power? If you define it as the ability to release energy quickly, gamma-ray bursts win. If you define it as sustained luminosity, quasars win. If you define it as gravitational influence, supermassive black holes win. If you define it as holding the universe together, dark matter wins. If you define it as shaping the universe's fate, dark energy wins. If you define it as binding matter at the smallest scales, the strong force wins. And if you define it as creating the conditions for everything, the Big Bang wins. Every answer depends on what you think power means, and that is the point. Because the universe does not care how we define power. It does not organize itself into a hierarchy of most powerful to least powerful. It does not rank forces by strength or events by energy output and then put a trophy on the shelf. The universe just is. It operates according to laws that we have spent centuries trying to understand, and those laws produce outcomes. Some of those outcomes are violent, some are gradual, some are invisible, some are foundational. They are all part of the same system. They are all connected. And the power of any one phenomenon is not separate from the power of the others. It is intertwined, dependent, emergent. A hypernova only happens because the strong force holds atomic nuclei together until a star runs out of fuel and collapses. The collapse only creates a black hole because gravity is strong enough to compress the core past the point where even neutron degeneracy pressure can hold it up. The black hole only grows by feeding on surrounding matter, which exists because nucleosynthesis in the Big Bang and fusion in earlier generations of stars created the elements. The surrounding matter only clumps into galaxies because dark matter provided the gravitational wells. The galaxies only have the structure they do because tiny quantum fluctuations in the early universe were amplified by inflation and then by billions of years of gravitational collapse. Every piece depends on every other piece. There is no single most powerful thing because power, in the cosmic sense, is not a property of individual objects or events. It is a property of the system, the universe as a whole. And here is where it gets strange, because the universe, as a system, produces outcomes that are far more complex than the rules governing it. The laws of physics are simple, elegant, 4 fundamental forces, a handful of particles, a few constants. You can write down the core equations on a single page, and yet from those simple rules you get stars, galaxies, planets, chemistry, life, consciousness. The ability to look up at the sky, detect the faint glow of the cosmic microwave background, decode the information it carries, and trace the history of the universe back to the first fraction of a second after the Big Bang. That capacity, that ability to understand, does not exist in the laws themselves. It emerges. It is not written into the equations. It is a consequence of the equations playing out over billions of years in a universe with the right initial conditions. This is what physicists and philosophers call emergence. The idea that complex systems can produce behaviors and properties that are not present in the individual components. Water molecules do not have the property of wetness. Wetness emerges from how water molecules interact in large numbers. Neurons do not have the property of thought. Thought emerges from how billions of neurons are connected and fire in patterns. And the universe, governed by simple laws, does not have the property of complexity written into it at the start. Complexity emerges over time. Through processes like star formation, nucleosynthesis, planet formation, chemical evolution, biological evolution, each step builds on the one before it. Each step adds a layer of structure that was not there initially, and the result, after nearly 14 billion years, is a universe that contains not just stars and galaxies, but also beings capable of wondering why any of it exists. That is the deepest kind of power, not the power to release energy or bend spacetime or hold matter together. The power to create conditions where complexity can emerge, where simple rules, applied consistently over vast stretches of time, produce outcomes that are far richer and more interesting than the rules themselves. The universe started with almost nothing, a hot, dense state, simple particles, unified forces, no structure, and it became this. A place with billions of galaxies, trillions of stars, countless planets, and at least one world where conscious beings can look up at the night sky and ask what it all means. That transformation, from simplicity to complexity, from uniformity to structure, from mindless particles to minds capable of understanding particles, is the most powerful thing the universe has done, not in a single moment, over its entire history. And the process is not finished. The universe is still expanding, still cooling, still evolving. Stars are still forming in molecular clouds. Planets are still coalescing from disks of gas and dust around young stars. Galaxies are still colliding, merging, triggering bursts of star formation. Black holes are still growing, still feeding, still shaping the galaxies around them. Dark energy is still pushing space apart, accelerating the expansion, driving the universe toward an eventual state where galaxies are too far apart to see each other and the cosmic web unravels into isolated islands. The story is not over. We are living in the middle of it. In a brief window where the evidence of the Big Bang is still visible, where stars are still abundant, where galaxies are close enough to study, where the universe is old enough to have produced complexity, but young enough that complexity can still thrive. In a few 100 billion years, that window will close. The universe will still be here, but it will look very different. The stars will have burned out. The black holes will have evaporated. The galaxies will have drifted beyond the cosmic horizon, their light stretched so far by the expansion of space that it will never reach observers in other galaxies. Future civilizations, if they exist, will have no way to know that the universe was once filled with stars, no way to detect the cosmic microwave background, no way to measure the Hubble constant or map the large-scale structure or confirm that the Big Bang ever happened. They will look out into the darkness and see almost nothing. They will think they live in a small, empty, eternal universe. They will be wrong, but they will have no way to know it. All the evidence will have disappeared over the horizon, carried away by the relentless expansion driven by dark energy. We are lucky. We exist at a time when the universe is still revealing its secrets, when the evidence is still here, when we can point telescopes at distant galaxies and see them as they were billions of years ago. When we can detect gravitational waves from black hole mergers and decode the information they carry. When we can map the cosmic microwave background and trace the evolution of the universe from the first fraction of a second to the present day. That is a gift, an accident of timing. We did not choose to exist in this era. We just do. And because we do, we have the opportunity to understand, to ask questions, to build instruments, to make measurements, to piece together the story of where we came from and where we are going. And that story, that understanding, is itself a form of power. Not the power to change the universe. We cannot do that. We cannot stop the expansion. We cannot prevent stars from dying, or black holes from evaporating, or dark energy from pushing galaxies apart. But we can understand it. We can see the connections. We can recognize that a hypernova in a distant galaxy and the atoms in our bodies are linked by the same processes. That the light from the cosmic microwave background and the thoughts in our minds are both consequences of the Big Bang. That the structure of spacetime and the structure of a living cell are both governed by the same fundamental laws. That power, in the deepest sense, is not about individual events or objects. It is about the system, the universe as a whole, the laws that govern it, the initial conditions that shaped it, the processes that built complexity from simplicity, the emergence of structure, consciousness, understanding. There is a scene that plays out every night, all over the world, that most people never stop to think about. Someone looks up at the sky. Maybe they are walking home from work. Maybe they are standing in a field. Maybe they are lying on their back in the grass. They see stars, faint points of light scattered across the darkness. And for a moment, they wonder, what are those? How far away are they? What is out there? That moment, that spark of curiosity, is the same spark that led ancient astronomers to chart the motion of planets, that led Galileo to point a telescope at the moon, that led Einstein to reimagine gravity, that led Hubble to discover the expanding universe, that led Penzias and Wilson to detect the cosmic microwave background, that led LIGO to capture gravitational waves, that led the James Webb Space Telescope to image galaxies at the edge of the observable universe. Every discovery, every breakthrough, every piece of understanding we have gained about the cosmos started with someone looking up and asking why. That is the human contribution to the story. We are not the most massive things in the universe. We are not the most energetic. We are not the longest lasting. We are brief, fragile, tiny specks of organized matter on a small rocky planet orbiting an ordinary star in an unremarkable galaxy. But we are the part of the universe that can understand the universe. We are the atoms that have learned to think, the matter that has become aware of itself, the product of 14 billion years of cosmic evolution that can look back at those 14 billion years and comprehend them. That is extraordinary. Not because it makes us powerful in the cosmic sense. We are not. A single gamma-ray burst pointed in our direction would sterilize the Earth in seconds, and the universe would not notice. But because it makes us aware, conscious, curious, capable of marveling at the fact that any of this exists at all, the universe does not need us. It got along fine for 13.8 billion years before the first humans appeared, and it will get along fine for trillions of years after the last human is gone. But we need the universe. Not just in the obvious sense that we are made of atoms forged in stars, and we live on a planet held together by gravity, and we breathe air made possible by billions of years of photosynthesis. But in the deeper sense that understanding the universe gives us context, perspective, a sense of scale, a reminder that the things we worry about, the things that feel overwhelmingly important in the moment, are happening on a stage so vast and so old and so indifferent to our concerns that the very fact we can think about it is miraculous. So when we ask what the most powerful thing in the universe is, the answer is not a single object or event. It is not a hypernova, or a gamma-ray burst, or a quasar, or a black hole, or dark energy, or the Big Bang. The most powerful thing in the universe is the universe itself, the system, the laws, the processes that turned a hot, dense, uniform state into a structured, complex, law-governed cosmos where complexity can emerge, where stars can shine, where planets can form, where life can begin, where minds can wonder. That is power, not the power of violence or destruction. The power of creation, of possibility, of existence itself. The power that allows anything, from the smallest quark to the largest galaxy cluster, from the briefest gamma-ray burst to the longest-lived black hole, from unconscious particles to conscious beings, to be here, to exist, to interact, to evolve, to matter, even if only to themselves. And we are part of that, not separate from it, not observers watching from the outside, part of it, made of the same atoms, governed by the same forces, subject to the same laws. We are what happens when the universe becomes aware of itself. When the atoms that were forged in the cores of dying stars and scattered across space by supernovae and gathered together by gravity into planets and mixed into molecules and arranged into cells and connected into brains, finally look up at the sky and recognize where they came from. That recognition, that understanding, that capacity to marvel is not an accident, it is a consequence. An emergent property of a universe with the right laws, the right initial conditions, the right history, and it is, in its own way, as powerful as anything else we have talked about. Because it is the thing that makes the universe comprehensible, the thing that turns raw existence into meaning, the thing that lets us see not just what is, but why it matters. The universe does not rule itself through a single force or object. It rules itself through the interplay of all its parts, through gravity pulling and dark energy pushing, through the strong force binding and the weak force transforming, through black holes devouring and stars creating, through galaxies colliding and matter clumping, through quantum fluctuations and cosmic expansion, through simplicity becoming complexity, through laws becoming outcomes, and through atoms, after billions of years of evolution, learning to ask questions. That is what rules the universe. Not power in the sense of dominance. Power in the sense of enablement. The power to make things happen, to create possibilities, to allow existence in all its forms to unfold. And we, for this brief moment in cosmic history, have the privilege of watching, of understanding, of marveling at the fact that it works at all. That is the real power, and it is still, right now, unfolding all around us. So here we are, standing on a small rocky planet orbiting an unremarkable star in the outer arm of a spiral galaxy containing hundreds of billions of other stars, most of which we will never see, in a universe containing hundreds of billions of other galaxies, most of which are already receding beyond the edge of what we will ever be able to observe. We have spent this entire video asking what the most powerful thing in the universe is, and the answer, if you have been paying attention, is that the question itself was wrong, because power is not a thing. It is not an object you can point to or an event you can measure. It is a property of relationships, of interactions, of systems. A hypernova releases more energy in 10 seconds than our sun will produce in 10 billion years. But that energy came from somewhere, from the star that built it over millions of years, from the fusion reactions powered by the strong force, from the gravitational collapse that compressed the core past the point of no return, from the initial conditions set by the Big Bang that determined which elements could form and how much matter would clump together into stars in the first place. The hypernova is not powerful in isolation. It is powerful because it is the endpoint of a chain of events stretching back to the beginning of time. The same is true for everything else. Gamma-ray bursts, quasars, black holes, dark matter, dark energy, the forces, the particles. Every phenomenon we have talked about is part of a web. Remove one thread and the whole structure changes. The universe does not have a single ruler. It is ruled by the interplay of everything within it, by laws that emerged in the first moments and have been shaping outcomes ever since, by the fact that those laws allow complexity to build from simplicity, structure from chaos, meaning from mechanism. And we are part of that web, not separate, not observers, participants, the universe looking back at itself and trying to understand how it got here. That capacity is fragile, brief, contingent on 1,000 things going right that could have gone wrong. But it is real, and it is happening now. Right now, as you hear these words, the atoms in your body, forged in the cores of dying stars billions of years ago, are arranged in a configuration complex enough to comprehend dying stars. That is the most powerful thing the universe has ever done. Not because it is violent, not because it is eternal, because it is aware. And awareness, however brief, is the thing that turns existence into experience. The thing that makes the universe not just a collection of particles,